Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're going to drift gently into one of the smallest, strangest, and most quietly important corners of the physical world, a place where matter is not solid in the way it seems, where the familiar objects around you are held together by invisible exchanges, and where a tiny particle called the pion helped physicists understand why the heart of the atom does not simply fly apart. The pion is not a particle most people meet in everyday conversation. It rarely appears on cereal boxes. It does not get the fame of the electron, the mystery of the neutrino, or the dramatic reputation of the black hole. You do not hear someone say, "I was late because of pions," although in a deep enough sense, pions are part of the reason there was a someone to be late in the first place. They belong to the quiet machinery beneath matter. They are part of the hidden world that keeps atomic nuclei bound, and therefore helps make stars burn, planets form, chemistry happen, and cups of tea remain cups of tea, instead of a drifting cloud of lonely particles with no sense of social commitment. So tonight, we will take our time with them. No rush, no sharp turns. We will not leap straight into particle physics as if we are trying to catch the last train home. We will begin softly, with the ordinary world, the world of stones, skin, water, wood, and air, and then slowly look beneath it. Because matter, when seen from a distance, feels dependable. A table feels like a table. A wall feels like a wall. Your blanket, I hope, feels like a blanket. But underneath that calm surface is a far busier story. Atoms are not tiny marbles stacked neatly in rows. Nuclei are not peaceful little clumps sitting quietly in the centre. They are crowded, energetic, stubborn places filled with protons and neutrons packed so closely together that, by ordinary intuition, they should not stay together at all. And that is where the question begins. Why does matter hold together? It sounds almost too simple at first. Matter holds together because it just does. The chair is there, the floor is there, the moon has not dissolved into a mist. Your hands do not pass through your teacup unless something has gone very wrong with either the teacup or the evening. But physics has a habit of taking the most obvious things in the world and revealing that they are not obvious at all. When we ask why the atom holds together, we quickly discover a puzzle. Inside the atomic nucleus are protons, and protons carry positive electric charge. Positive charges repel one another. They push away like two magnets turned the wrong way, or like two people both trying to leave a room through the same narrow doorway while being very polite about it. If the nucleus contains more than one proton, those protons should push each other apart, and yet they do not. Not usually. They remain bound together in the heart of the atom, packed into a space so tiny that our everyday sense of size gives up and quietly sits down. Something must be pulling them together more strongly than their electric repulsion pushes them apart. Something must be working inside the nucleus at very short distances with tremendous strength. That something is connected to the strong nuclear force, one of the fundamental forces of nature. And one of the first great clues to that force came through the pion. The pion is sometimes described as a messenger particle, although even that phrase can feel a little too human. It does not carry letters. It does not wear a small hat or knock politely on the door of a proton, but it can be understood as part of an exchange, a way that protons and neutrons communicate force between them. In older pictures of nuclear physics, the pion became the particle that helped explain how nucleons, the protons and neutrons inside the nucleus, attract one another and remain bound. It was not the final word because physics rarely gives us final words. Later, quarks and gluons revealed a deeper layer beneath the nucleus. But the pion remained deeply important. It was the first piece of a new language, one that helped physicists talk about how matter stays together at its core. Before we wander further inward, I would love to ask you something simple. Where are you listening from tonight, and what is around you right now? Maybe it is late where you are. Maybe the room is dim, and the day has loosened its grip a little. Maybe there is rain at the window, or a fan humming quietly, or the small glow of a screen nearby. Or maybe it is morning, and you're letting a bit of physics keep you company before the world becomes noisy. Wherever you are, it is strange and lovely to remember that the matter around you, the walls, the blanket, the floor, the air itself, is held together by forces we cannot see, arranged by particles we almost never think about, built from a depth of nature that is working faithfully whether or not anyone remembers its name. And if you find this journey soothing, interesting, or simply a gentle way to settle your thoughts, I would be ever so grateful if you gave the video a like and perhaps subscribed. It helps this quiet corner of science reach other curious night travellers, other people who like their physics served slowly, calmly, and with just enough mystery to make the universe feel larger without making bedtime feel impossible. I do hope tonight's subject does not keep you awake, but if it does, then at least you will be awake in the company of one of nature's tiniest glue-like mysteries, which is not the worst kind of company. A pion is small after all. It will not take up much room on the pillow. Now settle in. Let the idea of the ordinary world soften for a moment. You may be surrounded by familiar things, but every familiar thing is made of atoms, and every atom has a centre. That centre, the nucleus, is not large. In fact, compared with the whole atom, it is almost impossibly small. If the atom were expanded to the size of a large room, the nucleus would still be more like a speck somewhere in the middle than a heavy ball filling the space. And yet nearly all the atom's mass is concentrated there. The nucleus is tiny, but it carries the weight of matter. It is like finding that almost the entire weight of a house comes from a grain of sand hidden in one quiet corner. Inside that grain of sand, so to speak, are protons and neutrons. The protons help give the atom its identity. Hydrogen has 1, carbon has 6, oxygen has 8, gold has many more. The number of protons determines the element, and the element helps decide the character of matter. Change the number of protons, and you do not merely rearrange the furniture, you change the house. A different nucleus means a different atom, a different place on the periodic table, a different kind of chemistry, and eventually a different kind of world. But if protons repel each other, how can heavier nuclei exist at all? How can carbon hold 6 protons together? How can oxygen hold 8? How can gold hold so many, all packed into that tiny nuclear space, without bursting apart under their own electric dislike? The answer is that the nucleus is governed by a force far stronger than electricity at very short distances. It is not stronger everywhere. It does not reach across a room and pull your socks together, which is a shame because that would be extremely useful. But inside the nucleus, across distances so small that even imagination has to whisper, the strong interaction dominates. It binds protons and neutrons into nuclei, and without it, the universe would be almost unrecognizable. This is one of those moments where physics becomes both technical and deeply comforting. The world feels stable because there is an invisible agreement at its core, not a conscious agreement, of course. The proton does not wake up and choose teamwork. The neutron does not attend a committee meeting. But nature has rules, and those rules allow small things to bind into larger things to become atoms, atoms to become molecules, molecules to become cells, and cells to become listening minds wondering about pions in the dark. The pion entered the story because physicists needed a way to understand this binding. In the early 20th century, the nucleus was still a puzzle box. The neutron had been discovered. The proton was known. But the force that held them together remained strange. It had to be powerful. It had to be short-ranged. It had to overcome electric repulsion, but only inside the tiny domain of the nucleus. It could not behave like gravity or electromagnetism, whose influence can reach across huge distances. The nuclear force seemed almost private, active only when particles were extremely close. Like a secret handshake that only works if you're standing right beside someone. A Japanese physicist named Hideki Yukawa proposed that this force might be carried by a new particle. He imagined that protons and neutrons could attract one another by exchanging a particle of a certain mass. Not as heavy as a proton, not as light as an electron, but somewhere in between. This was a bold idea. At the time, the known particle world was still small. The particle zoo had not yet filled up with strange names and increasingly crowded diagrams. Suggesting a new particle was not casual. It was like hearing a strange creak in an old house, and calmly predicting that there must be a hidden staircase behind the wall. Yukawa's predicted particle was later connected with the Pion, also called the Pion meson. When particles discovered in cosmic rays began to fit the expected role, it was a remarkable confirmation that the nucleus could be understood through exchange. The force was not simply a mysterious pull, it could be pictured as arising from particles traded between particles, a kind of invisible conversation inside matter. That image is not perfect, and later theories would refine it, but it was powerful. It turned the nucleus from a silent knot into a place of motion, interaction, and exchange. The pion itself comes in different charged forms. There are positively charged pions, negatively charged pions, and neutral pions. They are not stable in the ordinary sense. They are short-lived, flickering into existence in high-energy processes and then decaying into other particles. You will not find a jar of pions on a shelf beside the sugar and the spare batteries. They appear in particle collisions, cosmic ray showers, nuclear interactions, and the intense environments where matter is pushed hard enough for its deeper parts to show themselves. Yet even though they vanish quickly, they play an important role in the way physicists understand the forces between nucleons. The name Pion sounds small and almost friendly, like it might belong to a tiny harmless creature in a children's book. But its meaning is tied to the strong force, to the architecture of matter, to the problem of why atomic nuclei exist. That is one of the nice things about physics. Sometimes the gentlest names belong to the deepest things. Electron, photon, pion. Each one sounds simple enough to say quietly while falling asleep, and yet each opens a door into an entire hidden world. To understand pions properly, we will need to travel through several layers of explanation. We will begin with matter as we know it, and the nucleus as the first great mystery. Then we will look at protons and neutrons, the crowded residents of the atomic center. We will meet Yukawa's idea and the prediction of a particle that had not yet been seen. We will follow cosmic rays into cloud chambers and photographic plates, where tiny tracks became evidence of invisible visitors. We will see why pions were once thought of as carriers of the nuclear force, and why modern physics places them in a larger story involving quarks, gluons, and the deeper strong interaction. And we will keep the pace gentle, because the inside of matter is already energetic enough. We do not need to hurry. For now, it is enough to hold the central picture softly in mind. The ordinary world is made of atoms. At the center of many atoms are nuclei. Those nuclei contain protons and neutrons. The protons should repel one another, yet the nucleus holds. The force that helps it hold is strong, short-ranged, and strange. And the pion was one of the first particles to reveal how that force might work between the building blocks of the nucleus. There is something almost tender about that idea, though we should be careful not to make particles sound sentimental. The pion is not emotional glue. It is not a tiny cosmic caretaker, but in the language of physics, it helped explain connection. It helped explain why separate things do not always remain separate. It helped show that the nucleus is not held together by stillness, but by exchange. Matter is not just made of objects sitting in place. It is made of relationships, fields, interactions, pushes, pulls, and fleeting messengers passing through the deepest rooms of reality. And perhaps that is why the pion deserves a little attention before sleep. It is not famous in the way some particles are famous. It does not dominate popular science headlines. It does not promise time travel, parallel universes, or a shortcut to understanding everything before midnight. But without the kind of physics it helped reveal, there would be no stable atomic nuclei beyond the simplest forms, no rich chemistry, no rocky worlds, no carbon chains, no long history of stars cooking heavier elements in their cores, no warm cup beside the bed, no listener wondering why matter holds together while the room grows quiet. So, as we begin, let the scale of things gently shift. Let the room around you become, in imagination, a landscape of atoms. Let every surface become mostly empty space, every object become a structure held together by forces, every solid thing become a kind of agreement between particles. Beneath the calm appearance of matter there is motion. Beneath the motion there are rules. Beneath the rules there are questions, and somewhere among those questions, small, brief, and deeply revealing, is the Pion, waiting at the edge of the nucleus, ready to lead us inward. Matter feels calm when we meet it at the human scale. A stone in your hand does not seem like an argument. A table does not seem like a negotiation between forces. A glass of water does not look as if it is being held together by a set of invisible rules that never once take a holiday. Matter simply seems to be there, steady, patient, dependable. It waits on shelves, rests under our feet, forms mountains, fills oceans, becomes skin and bone and leaf and candle wax and the soft cloth of a blanket. It is so ordinary that we rarely ask the most basic question about it. Why does it stay together at all? That question is easy to miss because our senses are not built to notice the hidden struggle inside things. We are built to notice whether the chair is strong enough to sit on, whether the soup is too hot, whether the door is closed, whether the floor is still where we left it. Our eyes and hands give us a world of surfaces, smooth, rough, cold, warm, heavy, light. But physics asks us to be a little impolite to appearances. It taps the surface gently and says, yes, but what is underneath? And underneath the calm surface of matter we find atoms. Underneath the atoms we find nuclei. And inside the nuclei we find a puzzle so strange that the solid world begins to feel less like a fact and more like a very successful balancing act. The atom is often introduced as if it were a tiny solar system, with a nucleus in the centre and electrons moving around it like planets around a star. It is a useful first picture, but it is also a little misleading. Electrons are not little planets following neat circular roads. They behave according to quantum rules, spreading out in patterns of probability rather than marching like beads on a wire. Still, the central idea is helpful. The atom has a dense centre, the nucleus, and around it is the much larger region where electrons are found. Nearly all the atom's mass lives in that central nucleus. The atom as a whole is mostly empty space, which sounds impossible until you remember that empty space at small scales is not the same as useless space. It is structured, active, ruled by fields and probabilities. It is not a blank room. It is more like a quiet room where something very precise is happening in the dark. The nucleus itself is made of protons and neutrons. Protons carry positive electric charge. Neutrons carry no electric charge overall. Together they form the compact heart of the atom. The number of protons tells us what element we are dealing with. 1 proton gives hydrogen, 2 gives helium, 6 gives carbon, 8 gives oxygen. 8. Many more gives the heavier elements, each with its own personality, its own chemistry, its own place in the long story of matter. That is already remarkable. The difference between the carbon in your body and the oxygen in the air begins with a count of protons inside a nucleus so small that it is far beyond direct experience. Nature builds variety from tiny differences in the most hidden places. But the nucleus should not be easy to build. If you put 2 positive electric charges near each other, they repel. They push apart. This is one of the basic lessons of electromagnetism. Like charges do not enjoy crowding together. They behave a little like 2 people trying to avoid sitting too close on an otherwise empty bus. In a nucleus, however, protons are packed extremely close together. In helium, there are 2 protons. In carbon, there are 6. In gold, there are many dozens. If electric repulsion were the only force in charge, the nucleus would not hold. the protons would shove each other away, and the elements that make the world rich and varied would never have had a chance to settle into existence. So there must be another force, something powerful enough to overcome the repulsion between protons at the tiny distances inside the nucleus. It cannot be gravity. Gravity is always attractive, and it is important on large scales, where planets, stars, and galaxies gather themselves under its influence. But between individual particles inside an atomic nucleus, gravity is unimaginably weak. It is the quietest whisper at a table where other forces are speaking much more loudly. Electromagnetism is strong enough to matter there, but it creates the problem rather than solving it, because it pushes protons apart. The weak force plays its own important role in particle change and radioactive processes, but it is not the glue that holds the nucleus together. What we need is the strong nuclear force. The strong force has a name that sounds almost too direct, like calling a mountain large or the ocean wet, but in this case the name is deserved. At the scale of the nucleus, the strong interaction is powerful enough to bind protons and neutrons together, despite the electric repulsion among the protons. It is the reason stable nuclei can exist. It is why atoms heavier than hydrogen are possible. It is why chemistry can become complicated. And because chemistry is the stage on which life performs its slow, strange play, the strong force sits quietly at the foundation of everything familiar. Without it, the universe would be a thinner, simpler, lonelier place. Yet the strong force has a curious habit. It is extremely strong at very short distances, but it does not reach far. You do not feel it tugging across the room. It does not pull the mug toward the bookcase or bind one chair to another. It is not like gravity, which reaches across space and keeps the moon moving around Earth. It is not like electromagnetism, which can act over long distances and send light across the cosmos. The strong nuclear force acts only when particles are extraordinarily close. It is more like a clasp than a rope, more like a handshake than a message shouted across a field. When protons and neutrons are close enough, the force can hold them. When they're too far apart, its grip quickly fades. This short range is one of the clues that led physicists toward the idea of a particle like the Pion. A force that reaches only a tiny distance suggests that whatever carries or represents that force has a certain kind of mass. In the early days of nuclear physics, scientists were trying to understand why the force inside the nucleus did not spread outward forever. If it were carried by a massless particle, like the photon carries electromagnetism, its influence might stretch much farther. But the nuclear force behaved differently. It was intense but local, strong but private. It did its work inside the nucleus, and then seemed to vanish almost immediately outside. To feel how strange this is, imagine trying to hold together a group of people standing in a circle. If they are close enough to lock arms, the circle holds. If they step back even a little, the connection breaks. The nuclear force is somewhat like that, though of course protons and neutrons do not have arms, and if they did, physicists would have much stranger diagrams to explain. The point is that closeness matters. At nuclear distances, attraction can win. Outside those distances, the force does not have enough reach to help. This is part of why nuclei have limits. Add more and more protons, and the repulsion grows. The strong force can still help, but only among nearby nucleons, while the electric repulsion among protons can accumulate across the nucleus. Very heavy nuclei become unstable, because the balance becomes harder to maintain. Neutrons play a crucial role in this balance. Since they carry no overall electric charge, they do not add to the electric repulsion between protons, but they do participate in the strong force. A neutron can help bind the nucleus without making the proton crowding problem worse in the same way. That is why heavier atoms usually need more neutrons than protons to remain stable. Neutrons are not just neutral passengers, they are part of the architecture. They help hold the nuclear crowd together, like calm guests at a lively dinner party who somehow prevent everyone else from leaving early. But even this picture is still only the beginning. Protons and neutrons are not fundamental in the deepest modern sense. They are made of quarks, held together by gluons through the strong interaction. The force between quarks is the underlying strong force described by quantum chromodynamics. That deeper theory is more exact, more modern, and much stranger. It tells us that protons and neutrons are not simple little balls, but dynamic systems filled with quarks, gluons, energy, and constant activity. A proton is not a quiet bead. It is more like a storm held in a shape. Still, when we talk about the force between protons and neutrons inside nuclei, the pion remains incredibly useful. It belongs to what we might call the leftover or residual strong force. Inside each proton and neutron, quarks and gluons are bound by the fundamental strong interaction. But outside them, between one proton and another, or between a proton and a neutron, there remains an effective attraction. The pion helps describe that attraction. It is not the whole story, but it is a vital clue, a bridge between the older picture of nuclear forces and the deeper modern picture of quarks and gluons. This can sound a little like saying there is glue inside the glue, which is not the most restful sentence ever invented, but it is close to the truth. The strong force holds quarks inside protons and neutrons. Then a residual effect of that strong force helps bind protons and neutrons together inside nuclei. The pion appears in this second level of binding like a messenger or exchange particle in the effective force between nucleons. If protons and neutrons are the bricks of the nucleus, the pion helps explain the mortar between them. And if that image feels too solid, remember that the mortar is not a substance smeared between tiny balls. It is an interaction, a process, a quantum exchange. Matter at this level is less like a pile of objects and more like a conversation that keeps successfully continuing. The word glue is helpful, but it can also trick us if we take it too literally. Ordinary glue is a sticky material. You spread it, press two surfaces together, wait a while, and hope you have not glued your fingers to the table. Nuclear glue is not like that. The particles inside the nucleus are not coated with a sticky film. They are bound by forces described through fields and quantum interactions. A pion is not a droplet of glue. It is a particle associated with the interaction between nucleons. It can be exchanged virtually in the way physicists describe forces, contributing to the attraction that keeps the nucleus from falling apart. The language of exchange is one of the great shifts in modern physics. Instead of thinking of a force as an invisible hand pulling directly, physicists learn to describe forces through fields and particles, through interactions that can be counted, calculated, and observed indirectly. This idea changes the feel of reality. A force is not merely a push or pull that happens from nowhere. It is part of a deeper structure. In the quantum world, fields fill space, and particles are excitations of those fields. The electron belongs to the electron field. The photon belongs to the electromagnetic field. Pions belong to fields connected with the strong interaction and the behavior of quarks. They arise in the nuclear world as short-lived particles with just the right character to help explain the short-range attraction between nucleons. They are not permanent fixtures in the nucleus like furniture in a room. They are more like passing notes in a very busy conversation, appearing and disappearing as the interaction unfolds. And yet, from that fleeting activity comes stability. This is one of the great surprises of physics. Permanence at our scale often comes from motion at a smaller scale. A solid object looks still because its inner processes are balanced, not because nothing is happening. An atom remains an atom because the interactions within it follow stable patterns. A nucleus remains a nucleus because the forces inside it hold together under the right conditions. The stillness of matter is an illusion created by activity too small and too fast for our senses to track. Your hand resting on a blanket feels quiet, but within the atoms of both hand and blanket there is structure, vibration, quantum behavior, and nuclear binding. The calm is real, but it is a calm built from motion. Think of a spinning top. When it spins steadily, it can look strangely stable, almost serene, but its stability depends on motion. slow it down too much, and it wobbles and falls. Matter has a similar kind of hidden balance. It is not held together because everything inside it has stopped. It is held together because forces and motions arrange themselves in ways that produce stable forms. The Pion, in the old and still useful description of nuclear binding, belongs to that hidden balancing act. It helps us understand why the nucleus does not simply surrender to the repulsion of its protons. This matters not only for the atom, but for the history of the universe. In the first moments after the Big Bang, matter was hot, dense, and wild. As the universe expanded and cooled, protons and neutrons formed. Later, some of them combined into light nuclei. Much later, inside stars, nuclear reactions built heavier elements. Every stage depended on nuclear forces. If the strong interaction had been much weaker, nuclei might not have formed in the same way. If it had been much stronger or behaved differently, stars and elements might have followed a completely different story. The balance is delicate. We live in a universe where the rules allow complexity, and the strong nuclear force is one of the main reasons that complexity can exist. There is a gentle awe in realizing that the same kind of force that binds atomic nuclei also makes the periodic table possible. The carbon in living things, the oxygen we breathe, the calcium in bones, the iron in blood, the silicon in rocks, the gold in rings, all of these require nuclei that can hold together long enough to become part of the world. We often think of matter as a collection of ingredients, but before there can be ingredients, there must be stable nuclei. Before chemistry can write its long recipes, nuclear physics must provide the letters. The Pion helped physicists understand part of how those letters stay on the page. The atom does not fall apart because several forces cooperate and compete across different scales. Electrons remain bound around nuclei through electromagnetism and quantum rules. Nuclei remain bound through the strong force. Neutrons help stabilize the crowded nuclear interior. Protons define the element while also creating electric repulsion that must be overcome. The whole structure is not simple, but it is beautifully layered. Each level has its own rules, and each level depends on the one beneath it. The world of chemistry rests on the world of atoms. The world of atoms rests on nuclei and electrons. The world of nuclei rests on nucleons and the forces between them. And within that hidden depth, the Pion appears as one of the first great signs that matter is held together, not just by things, but by exchanges between things. It is also worth remembering that the Pion was not invented to make the story prettier. It was proposed because the nucleus demanded an explanation. Physics is at its best when it listens carefully to a problem. The nucleus said, in effect, I should not be stable if you only count the forces you already know. So physicists had to look deeper. They needed a force strong enough to bind, short-ranged enough to stay confined, and strange enough to fit the evidence. Yukawa's idea of a force-carrying particle was a way of answering that demand. Later discoveries showed that nature really did contain particles in the right mass range, and with the right behaviour to match the picture. The Pion was not just a clever thought. It became part of the evidence that the hidden glue of matter could be understood. Of course, like many scientific answers, it opened new questions. If the Pion helps explain the force between protons and neutrons, what is the Pion made of? Why does it have the properties it does? How does it fit into the deeper world of quarks? Why are there different kinds of pions? Why do they decay so quickly? Why does the strong interaction behave so differently from electromagnetism? Every answer in physics is a door with another door behind it, but that is not a failure. That is the charm of the place. The universe does not reveal itself all at once. It gives us handles. The Pion was one of those handles, small, brief and easy to overlook, but strong enough to pull open part of the nuclear world. So when we ask why the atom does not simply fall apart, the answer is not one sentence. It is a layered story. The atom survives because its electrons are arranged by quantum rules around the nucleus. The nucleus survives because the strong force binds its protons and neutrons together. The protons do repel one another, but at very short distances the nuclear attraction can overcome that repulsion. Neutrons help provide binding without adding electric charge, and in the effective picture of nuclear forces, pions help carry or describe the attraction between nucleons. They are part of the hidden conversation that keeps the nucleus from becoming a scattering of pieces. That may be the most important shift for tonight. Matter is not held together by stillness. It is held together by interaction, not by silence, but by a kind of microscopic conversation. The world feels solid because the conversations are reliable. The nucleus holds because the rules are consistent. The table remains a table because its atoms remain atoms, and its nuclei remain nuclei, and deep inside those nuclei the strong force continues doing its quiet work. The ordinary world is resting on extraordinary discipline, so the next time you touch something solid, a book, a cup, the edge of a pillow, you might imagine for just a moment the hidden architecture beneath your fingers. Not a dead structure, not a pile of tiny stones, but a living pattern of forces in the physical sense, active and balanced, with particles and fields maintaining the forms we take for granted. Somewhere below chemistry, below atoms, below the soft certainty of everyday matter, there is the nuclear realm, short-ranged, intense and crowded. And to understand that realm more clearly, we need to look more closely at the residents of the nucleus itself, the protons and neutrons, and the strange force that binds them into the dense little centres from which the visible world is built. To understand why the pion mattered so much, we need to spend a little more time with the nucleus itself. Not as a neat dot in a school diagram, and not as a simple little ball at the centre of the atom, but as a crowded, restless, highly organised place where some of the strongest forces in nature are quietly at work. The nucleus is small beyond ordinary imagination, but it is not simple. It is dense, busy, and surprisingly dramatic for something that spends most of its time hiding at the centre of things like spoons, stones, houseplants, and sleepy human listeners. At first glance, the nucleus seems as if it should be easy to describe. It contains protons and neutrons. Protons have positive electric charge. Neutrons have no overall electric charge. Put them together, and you have the centre of an atom. That sounds tidy enough, almost like sorting buttons into a jar. But the moment we look more carefully, the jar begins to rattle. Protons and neutrons are not smooth, hard pellets. They are not little grains of matter with clear edges and peaceful interiors. They are composite particles, built from quarks, held together by gluons, filled with motion and energy. Even a single proton is not really still. It is a dynamic object, if object is even the right word, with its inner parts constantly interacting. This can be a little uncomfortable, because our minds like objects to be simple. A pebble is a pebble, a button is a button, a crumb on the table is, depending on your mood, either something to clean up or a snack for later. But the subatomic world does not care much for our tidy categories. A proton is not a tiny billiard ball. A neutron is not a proton painted grey. They are patterns of energy and interaction, stable enough to build atoms, but not simple enough to be understood as miniature everyday objects. They belong to a world where matter is not made of little solid pieces, so much as it is made of relationships that keep working. Still, for the purpose of the nucleus, protons and neutrons are often treated together as nucleons. That word simply means the particles that live inside the nucleus. It is a useful word because protons and neutrons behave in many ways like close relatives. They have almost the same mass. They both participate strongly in the nuclear force. They both help form atomic nuclei. And in some nuclear processes, one can even transform into the other through the weak interaction. So while they are not identical, they are similar enough that the nucleus treats them as members of the same small family. Though as with many families, the details are where things get interesting. The proton is the more famous of the two. It gives the atom its identity. Count the protons, and you know the element. 1 proton means hydrogen, 2 means helium, 6 means carbon, 8 means oxygen. Every element is defined by this count. If you change the number of protons, you change the element itself. Add 1 proton to carbon, and you no longer have carbon, you have nitrogen. Remove 1 from oxygen, and you have nitrogen again, which is a reminder that the periodic table is less like a shelf of separate objects and more like a set of identities written in nuclear numbers. The neutron at first seems quieter. Since it has no overall electric charge, it does not announce itself as loudly through electromagnetic forces. But quiet does not mean unimportant. In fact, neutrons are essential for the stability of many nuclei. They help provide strong nuclear attraction without adding extra positive electric repulsion. In heavier atoms, this becomes crucial. A nucleus with many protons needs neutrons to help hold the structure together, a little like adding calm, steady support beams inside a crowded room where everyone else is pushing away from everyone else. Without enough neutrons, many nuclei become unstable. With too many, they can also become unstable. The nucleus is not a place where more is always better. It is a place of balance. This balance is delicate because 2 different forces are pulling the story in opposite directions. The electric force pushes protons apart. The strong nuclear force pulls nucleons together, but only when they're very close. This is the heart of the nuclear puzzle. Protons repel each other because they carry the same kind of electric charge. That repulsion does not politely disappear just because the protons are inside a nucleus. It is still there. It is still trying to separate them. But the strong force acting over very short distances can overpower it. In the tiny space of the nucleus, attraction wins, at least for stable nuclei. There is something almost strange about the short range of the nuclear force. Gravity reaches across the universe. Electromagnetism reaches across space too, carrying light from distant stars into our eyes. But the force that binds the nucleus is more private. It works only across distances so small that even the atom seems huge by comparison. Move the nucleons too far apart and the force fades rapidly. Bring them close enough and suddenly it becomes powerful. This is not the behavior of a force we can easily picture from daily life. It is not like a rubber band stretching across a room. It is more like a lock that only clicks shut when the pieces are pressed almost exactly together. That short range is part of what makes the nucleus so dense. Protons and neutrons have to be close for the strong attraction to matter. The nucleus is not spread out loosely through the atom. It is packed tightly at the centre. Nearly all the mass of the atom is concentrated there, while the electrons occupy a much larger surrounding region. If an atom were enlarged to the size of a cathedral, the nucleus would still be a tiny dense speck within it, and yet that speck would carry almost all the weight. The rest would be space-shaped by quantum rules, with electrons arranged not as tiny planets, but as probability patterns around the centre. So the nucleus is small, heavy, and held together by an intense short-range force. But there is another twist. The strong nuclear force between protons and neutrons is not the most basic form of the strong interaction. In modern physics, the deeper strong interaction acts between quarks and gluons inside protons and neutrons. Quarks carry a kind of charge called color charge, and gluons are the particles associated with the strong force at that deeper level. This is the realm of quantum chromodynamics, a theory with a name that sounds like someone spilled paint into a physics textbook. The colour in color charge has nothing to do with ordinary colour. Protons are not secretly red, green and blue in the way apples or traffic lights are. The names are labels for a kind of mathematical property, which is not as cosy as a blanket, but very useful if you're trying to describe the deep structure of matter. Inside a proton or neutron, quarks are held together so strongly that they are never found alone under ordinary conditions. Try to separate them, and the energy involved does not simply let one quark drift away like a loose bead from a necklace. Instead, new particles form. The strong interaction has this unusual feature called confinement. Quarks remain bound within larger particles such as protons, neutrons, and pions. This means that the familiar protons and neutrons inside nuclei are themselves little bundles of strong force activity. They are not the deepest floor of the building. They are already rooms with busy machinery inside. The force between nucleons, the force that helps bind the nucleus, can be thought of as a leftover effect of that deeper strong interaction. A useful comparison is the way neutral atoms can still attract one another through subtle electromagnetic effects, even though each atom as a whole has no net charge. The details are different, of course, and the nuclear case is much stronger and much stranger. But the general idea is that something powerful inside the nucleons leaves an effect outside them, allowing protons and neutrons to attract one another. This leftover strong force is what early nuclear physicists were trying to describe when they began thinking about exchange particles such as the pion. Before the pion entered the story, the nucleus was a kind of locked box. Physicists knew that protons and neutrons were there. They knew that nuclei could be stable. They knew that electric repulsion should make stability difficult, especially in heavier elements, so they needed a mechanism. They needed to explain how the force worked, why it was so strong, and why it did not reach far beyond the nucleus. It was not enough to say, well, the nucleus stays together because it stays together. Physics is rarely satisfied with that kind of answer, although it would make textbooks much shorter and probably easier to carry. The idea that forces could be explained by exchanging particles was becoming one of the central ideas of 20th century physics. In electromagnetism, light particles called photons are associated with the electromagnetic force. In the nuclear case, Hideki Yukawa suggested that the force between protons and neutrons might also be carried by a particle. But this particle could not be massless like the photon, because the nuclear force did not have an infinite reach. It had to be short-ranged. Yukawa reasoned that a particle with a mass between that of the electron and the proton could explain the range of the nuclear force. That predicted particle would eventually be connected with the pion. This was an elegant idea because it matched the personality of the nuclear force. A heavier exchange particle would make the force short-ranged. It would appear, do its work, and not carry influence across large distances. The nucleus could remain a tiny domain where the strong force mattered deeply, while the everyday world outside would not be dominated by it. This helps explain why you do not notice the strong nuclear force directly when you move through a room. It is not absent. It is simply locked away at the scale of nuclei, where its reach is tiny and its strength is enormous. The proton and neutron are also affected by something called isospin, though we can keep that idea gentle. In early nuclear physics, protons and neutrons seemed so similar under the strong force that physicists treated them as two states of a single kind of particle, the nucleon. The proton had electric charge, the neutron did not, but the strong force treated them almost as variations on a theme. This helped scientists build mathematical descriptions of nuclear interactions. The pion fit naturally into this kind of thinking because it came in different charge forms, able to connect the behavior of protons and neutrons in the nuclear force. It was as if nature had provided not just one messenger, but a small set of related messengers, each suited to a slightly different exchange. The charge pions and the neutral pion help describe interactions among nucleons. A proton might become a neutron by emitting a positively charged pion in a simplified picture, while another nucleon absorbs it. A neutron might become a proton through related exchanges. The exact modern treatment is more subtle, and we should not imagine tiny particles flying like tennis balls between hard spheres in a literal classical way. Quantum fields are not a game of catch in a garden. Still, the image is helpful if we hold it lightly. The pion represents a way for the nucleons to interact, to exchange energy and momentum, to feel the attraction that helps the nucleus hold. One of the challenges in understanding the nucleus is that it is not just a two-particle problem. A simple hydrogen nucleus has only one proton, so there is no crowd of nucleons to bind together. But heavier nuclei contain many protons and neutrons. Each nucleon interacts with nearby nucleons. The strong force is short-ranged, so each one mostly feels those close to it, while the electric repulsion between protons can act across the whole nucleus. This creates a complex balance. Smaller nuclei can be very stable. Larger nuclei require more neutrons and become increasingly difficult to hold together. At the far end of the periodic table, heavy nuclei may decay, split, or transform because the balance cannot last forever. This is why radioactivity exists in some nuclei. It is not because the nucleus is broken in a simple way. It is because the internal balance of forces and particles is unstable. Some nuclei have too many neutrons, some have too few. Some are too heavy for the strong force to keep them comfortably together against the growing electric repulsion. The nucleus then changes, releasing particles or energy, moving toward a more stable arrangement. Even instability in physics follows rules. It is not chaos in the careless sense. It is nature looking for a better balance. The strong force also explains why nuclear energy can be so powerful. Chemical reactions involve electrons and the electromagnetic arrangements of atoms. Nuclear reactions involve changes in the nucleus itself. Since the forces inside the nucleus are much stronger, changes there can release far more energy. This is why the sun shines through nuclear fusion. In the sun's core, light nuclei combine under extreme heat and pressure, and the resulting changes release energy that eventually reaches Earth as sunlight. Every warm afternoon, every green leaf, every quiet patch of sun on a windowsill is connected to nuclear forces operating deep inside a star. The strong force may be hidden, but its consequences are spread across every daylight hour, and yet the force remains strange. It is strong but short-ranged. It binds, but only under the right conditions. It emerges from a deeper interaction among quarks and gluons, but at the level of protons and neutrons it can be described through particles such as pions. It is responsible for stability, but it also helps shape decay and transformation. It is one of the great examples of how nature can be simple in principle and complicated in practice. The rule exists, but its consequences depend on the arrangement, the distance, the particles involved, and the energy of the system. At this point, it may help to return to something familiar. Imagine a crowded room where people are standing close together. Some pairs are drawn into conversation. Some pairs would rather keep their distance. If everyone were pushing away from everyone else, the room would empty quickly. If everyone were only attracted to everyone else across any distance, the room might collapse into a very uncomfortable pile near the centre. But if strong connections work only at close range, and repulsions behave differently, the crowd can form patterns, clusters can hold, groups can become stable or unstable, depending on how many people are present and how they are arranged. The nucleus is not a social gathering, of course, and protons do not make small talk near the snack table. But the idea of competing tendencies is useful. Stability is not the absence of forces. Stability is what happens when forces balance in the right way. This is what the nucleus teaches us. The centre of the atom is not peaceful because nothing is happening. It is peaceful because many things are happening in a way that holds together. Protons repel through electromagnetism. Protons and neutrons attract through the strong nuclear force. Neutrons add binding without adding electric repulsion. The short range of the strong force prevents it from dominating everyday distances. The deeper structure of quarks and gluons gives rise to the nucleons themselves, and pions help describe the effective attraction between those nucleons, giving physicists one of their first clear pictures of how the nuclear force could work. The more we study protons and neutrons, the less they seem like simple building blocks, and the more they seem like weather systems, stable patterns inside a deeper field of activity. A proton has a long lifetime and a reliable identity, but inside it, quarks and gluons are always interacting. A neutron inside a stable nucleus can remain part of matter for ages, but a free neutron outside a nucleus will decay after a short while. The same particle can behave differently depending on its situation. Context matters, even in particle physics, perhaps especially in particle physics. So when we say the nucleus contains protons and neutrons, we're saying something true but incomplete. It is like saying a city contains buildings and roads. True enough, but it leaves out traffic, Electricity, conversations, water pipes, arguments, meals, deliveries, and someone somewhere trying to find their keys. The nucleus contains protons and neutrons, yes, but also forces, exchanges, quantum fields, binding energies, possible decays, and hidden structures inside each nucleon. The Pion belongs to this richer picture. It appears when we stop treating the nucleus as a static clump and begin treating it as an active system. That active system is responsible for the existence of nearly everything around us. Stable nuclei allow atoms to persist. Atoms allow molecules. Molecules allow solids, liquids, gases, crystals, proteins, oceans, planets, and eventually the quiet act of listening. The strong force inside the nucleus is not something separate from everyday life. It is simply buried far beneath the scale where everyday life notices it. Like the foundations of a house, it is not usually visible, but everything above depends on it remaining sound. Now the stage is set for the Pion to step more clearly into view. We have the crowded nucleus. We have the positively charged protons pushing apart. We have the neutrons helping stabilize the structure. We have the strong force acting powerfully, but only across tiny distances. And we have the need for a messenger, a particle that could explain why this force has the range and strength it does. The Pion did not arrive as a random addition to the particle list. It arrived as an answer to a very specific problem, a missing piece in the attempt to understand how the nucleus holds together at all. To see why physicists expected it before they clearly identified it, we need to follow the logic that led from the strange force inside the nucleus to the prediction of a particle too small and too brief to meet directly, yet important enough to change the way matter itself was understood. The nucleus, as we've seen, is not a quiet little bead sitting politely at the centre of the atom. It is crowded, compact, and held together by a force that seems almost custom-built for the job, strong enough to overcome the electric repulsion between protons, but short-ranged enough that it does not reach out and glue the whole room together, which is probably for the best. If the strong nuclear force worked at everyday distances, opening a cupboard might become a major engineering project, and getting out of bed could require a research grant. So physicists faced a very specific mystery. There had to be something happening between protons and neutrons inside the nucleus, not something vague. Not simply a word like attraction placed over the problem like a blanket. They needed to understand how the attraction worked. Why did it act only at tiny distances? Why did it bind protons and neutrons so powerfully once they were close? Why did it disappear so quickly beyond the nuclear scale? A force this important could not remain a nameless tug in the dark forever. It needed a mechanism, a picture, a way for the human mind to hold it without dropping it immediately. The Pion entered this story as a kind of messenger. Now, messenger is a helpful word, but it should be treated gently. A Pion is not a little courier wearing a cap, hurrying from one proton to another with a folded note that says please remain bound. It is not a miniature postal service operating inside the atom, although if it were, one imagines the delivery times would be impressively short. In physics, when we call a particle a messenger, we mean that it can be associated with the way a force is transmitted between other particles. It is part of the interaction. It helps represent the exchange that allows one particle to feel the presence of another. This idea may sound strange at first because in daily life, forces do not usually seem to need messengers. Push a door and it opens, pull a blanket and it slides, drop a spoon and gravity takes over without apparently sending anyone to explain the situation to the floor. But modern physics gradually revealed that force is not just mysterious, invisible commands. At a deep level, they can be described through fields, and in quantum theory, those fields are associated with particles. The electromagnetic force is associated with the photon. The strong interaction, at its deepest quark and gluon level, is associated with gluons. And the nuclear attraction between protons and neutrons can be described in an effective way through the exchange of particles such as pions. That word exchange is central. Imagine two ice skaters facing each other on smooth ice. If one throws a ball to the other, both skaters move slightly because momentum has been transferred. The thrower moves backward, the catcher moves too, and the exchange changes their motion. This simple picture is often used to help explain how particles can affect one another by exchanging other particles. But the nuclear case is more subtle than a ball thrown across a rink. The quantum world does not work like a winter sports demonstration arranged for a school assembly. The exchange pion is not necessarily a little object flying in a neat visible path between two hard spheres. It belongs to a field description, a mathematical and physical process that is harder to picture directly. Still, the idea of exchange gives us a doorway. It tells us that force is not just a static rope between particles, it is an active interaction. The pion is suited to the nuclear force because it is not massless. This matters. A force carried by a massless particle can have a very long range. Light can travel across the universe because photons are massless. The electromagnetic influence can extend very far, weakening with distance but never simply dropping away at the scale of an atomic nucleus. The nuclear force is different. It acts across a tiny range and then fades. A particle with mass can help explain that short range. The pion has mass but not as much as a proton or neutron. It sits in a middle region, heavier than the electron, lighter than the nucleons it helps connect. In the early days, this made it seem like exactly the kind of particle that could fit the nuclear mystery. The name pion comes from meson. A meson is a particle made from a quark and an antiquark. That modern description came later, after the deeper quark model was developed. But even before physicists understood its inner makeup, the pion was recognized as belonging to a new kind of particle. It was not an electron, it was not a proton, it was not a neutron. It was something different, something that lived briefly and appeared in high-energy events, something whose existence helped make sense of the short-range force inside the nucleus. It was a sign that the particle world was not limited to the few familiar pieces known at the beginning of the 20th century. Nature had more characters waiting in the wings, and some of them were very shy. There are three main kinds of pion. There is a positively charged pion, a negatively charged pion, and a neutral pion. These names are straightforward enough, and one might almost be grateful for them. Particle physics often has names that sound as if they were invented during a very long meeting with too much coffee. But the pion names tell you something important right away. Some pions carry electric charge. One carries no electric charge overall. This matters because protons and neutrons are related by the strong force in a way that allows charged pion exchange to change one into the other in simplified descriptions. A proton can be linked to a neutron through the exchange of a charged pion, and a neutron can be linked back through a related process. Again, we must not picture this too literally, as if particles are passing marbles back and forth in a tiny game. But as a guide, it helps. The neutral pion has its own role. It can be involved in interactions where the identities of the nucleons do not change in the same way. It is also famously short-lived, decaying almost immediately into photons. To say almost immediately is, at the pion scale, still much too relaxed. Its lifetime is so brief that ordinary time language begins to feel oversized, like using a grandfather clock to time the flap of a moth's wing. Charged pions live longer than neutral pions, but even they are fleeting by human standards. They appear, interact, decay, and leave behind other particles. If you tried to wait for a pion to settle down and introduce itself properly, it would already be gone. This short life is part of why pions are too small and too brief to see directly. No one peers through a microscope and watches a pion sitting there like a dust speck on glass. The subatomic world does not offer itself to the eye in that way. Instead, physicists infer particles through their effects. They look at tracks, decay products, energy deposits, patterns in detectors, and the ways particles transform. It is a little like knowing a bird passed through a snowy garden, because you see the footprints, the disturbed branch, and the tiny marks of wings. You did not see the bird land, but the evidence is written in the snow. In particle physics, the snow is often a detector, a photographic plate, a cloud chamber, a bubble chamber, or a modern electronic instrument filled with layers of carefully designed material. The Pion is known by what it does. The idea of seeing by effect is not unique to particle physics. We know the wind by the movement of leaves. We know a person walk through a room by the creak of a floorboard, or the door left slightly open. We know time has passed by the cooling of tea, the dimming of light, and the suspicious disappearance of biscuits. Much of science works this way. The deeper something is, the more often we meet it through traces rather than direct contact. The Pion is one of those trace makers, one of those hidden actors whose presence is revealed not by a face, but by consequences. Inside the nucleus, the Pion helps describe how protons and neutrons interact. This is often called the pion exchange picture. In this picture, the force between nucleons comes from the exchange of pions. A proton and a neutron can exchange a pion, and through that exchange feel an attraction. The exchange pion does not last as a free particle. It is part of the interaction itself, allowed within the rules of quantum theory as a virtual particle. Virtual here does not mean fake in the everyday sense. It does not mean imaginary or pretend, like a virtual pet that has somehow survived on a dusty old computer. It means a particle involved internally in an interaction, not directly observed as a free incoming or outgoing particle. Virtual particles are part of how physicists calculate and describe quantum processes, and they can have real measurable consequences even if they are not caught as standalone particles. That can sound slippery, but the important point is simple enough. In the quantum world, interactions are not always made from particles we can isolate before and after the event. Some particles appear as internal features of the process. The pion, in the nuclear force between nucleons, can be understood this way. It helps represent the attraction between them. It is part of the hidden machinery, not a long-lasting resident strolling around the nucleus. The nucleus is not full of pions sitting in rows like passengers waiting for a train. It is better to think of pion exchange as a pattern of interaction that helps hold the nucleons together. And here we find one of the lovely paradoxes of the pion. It is fleeting, yet it helps explain stability. It exists briefly, yet it contributes to the long-lived structure of matter. It cannot be seen directly, yet its effects help shape the visible world. A particle too short-lived to meet can still be part of why ordinary things endure. That is very much the style of the subatomic world. The things that last at our scale are often supported by things that do not last at theirs. The Pion also helped physicists realize that the nucleus was not merely a collection of protons and neutrons glued by some mysterious unnamed substance. It was an interacting quantum system. Its binding could be studied through particle exchange. Its behavior could be modeled, predicted, compared with experiments. That shift was enormous. It moved nuclear physics from a descriptive puzzle toward a deeper theory of interactions. Before the Pion, the nuclear force was a shadow with a name. After the Pion, it began to have a voice. Of course, the Pion was not the whole answer. Later discoveries revealed that protons and neutrons are made of quarks, and that the fundamental strong force is carried by gluons between those quarks. In that deeper picture, pions are not fundamental force carriers in the same sense that photons are for electromagnetism. They are composite particles. They are made from quark and antiquark pairs. The force between nucleons can be understood as a residual effect of the more fundamental strong interaction. But this does not make the Pion unimportant. In fact, it makes it more interesting. It becomes a bridge between layers of reality. It connects the older nuclear picture to the deeper quark picture. It is not the final foundation, but it is one of the most useful stepping stones. Sometimes science progresses exactly like that. An idea arrives, explains a mystery, and later becomes part of a larger framework. Newton's gravity was not thrown away when Einstein described curved space-time. It remains useful and accurate in many situations. In the same way, the pion exchange picture remains important for understanding nuclear forces, even though quantum chromodynamics gives a deeper account. The pion is not an outdated character shuffled off the stage. It is still there, helping us speak clearly about the low-energy behaviour of the strong force between nucleons. The reason pions are so useful is that they are closely connected to the symmetries of the strong interaction. We do not need to go deeply into that mathematical forest tonight, because this is a gentle journey and not a blackboard interrogation. But the basic idea is that pions are not random particles. They arise naturally from the way quarks and the strong force behave. They are light compared with many other hadrons because of deep symmetry patterns in quantum chromodynamics. Their existence tells us something about the structure of the strong force itself. They are not just little messengers tossed into the story to solve a problem. They are clues to the deeper order beneath the nucleus. A pion can also be created in high-energy collisions. When particles smash together with enough energy, new particles can emerge, and pions are among the most commonly produced. They appear in cosmic ray showers when high-energy particles from space strike atoms in Earth's atmosphere. They appear in particle accelerators when protons or other particles collide. In these events, pions often decay into muons, neutrinos, photons, and other particles depending on their type. Their tracks and decay patterns have taught physicists a great deal about particle interactions. But that part of the story, the discovery and detection of pions, comes with its own set of cloud chambers, mountain laboratories, photographic plates, and patient scientists staring at tiny trails. We will walk there soon enough. For now, we are meeting the pion as an idea entering the nuclear problem. And what an idea it was. Imagine trying to explain why the nucleus holds together, knowing that protons repel, knowing that the force must be strong and short-ranged, and then suggesting that there is an unseen particle responsible for the exchange. Not an ordinary particle already known, but a new one, a particle with just the right mass range to explain the range of the force. A particle that would live too briefly to be part of everyday matter, but not too briefly to shape the interactions at matter's core. This was not just adding a name, it was changing the style of explanation. It said the nucleus is not held together by a static glue, but by quantum exchange. There is a calm beauty in that. The visible world looks solid because invisible exchanges happen reliably. The surface of your desk, the pages of a book, the bones in your hand, the oxygen in your lungs, all depend on stable atoms. Stable atoms depend on stable nuclei. Stable nuclei depend on the strong attraction between nucleons, and the pion helped reveal one way to understand that attraction. At the bottom of solidity, we do not find stillness. We find communication. Not communication with words, not meaning, not intention, but interaction. The universe holds itself together by exchanging pieces of itself. This is why calling the pion a messenger is both imperfect and useful. It is imperfect because particles do not send messages the way we do. There is no plan, no sender, no receiver in the human sense. But it is useful because it captures the idea that forces are relational. A proton does not simply sit alone with a property called attraction floating around it. It interacts. It participates in fields. It exchanges. It belongs to a network of possible processes. The pion is one of the ways that network becomes visible to understanding. For a listener drifting towards sleep, this may seem like a rather small thing to spend time on. A tiny particle, short-lived, invisible, hidden inside a force that itself hides inside the nucleus. But smallness is not the same as insignificance. The roots of a tree are hidden too, and so are the foundations of a house. The brain does not see its own neurons working, yet thought depends on them. The world is full of things that matter precisely because they do their work out of sight. The pion belongs to that quiet class of importance, and perhaps that is the right way to hold it for now. The pion appears not as a famous celebrity particle, but as a necessary whisper in the nuclear conversation. It tells us that the strong force between protons and neutrons can be understood through exchange. It tells us that a force may have range and character because of the particles associated with it. It tells us that the nucleus is dynamic, not static. It tells us that the matter we trust under our hands is supported by processes too small to see, too quick to follow, and too precise to be accidental. So, as we move further into the story, keep the Pion in mind as a tiny messenger that cannot be seen directly, yet leaves a strong signature in the way nuclei behave. It is a particle of the between space, not in the everyday sense of empty space between objects, but in the relational space between nucleons. It belongs to the attraction, to the binding, to the hidden reason protons and neutrons remain together when they might otherwise part ways. And once this idea of a nuclear messenger was placed on the table, the next question became unavoidable. Who first imagined it? And how could anyone predict a particle before nature had clearly shown it to us? The question was not simply whether a new particle might exist. It was whether the nucleus itself was quietly demanding one. By the early decades of the 20th century, physicists had already learned enough to be properly confused. They knew that atoms had small dense nuclei. They knew that nuclei contained protons. They had discovered the neutron, which solved some problems while politely opening several more. They knew that protons pushed one another apart through electric repulsion. And yet, there they were, packed tightly together inside atomic nuclei, not flying away like offended guests leaving a crowded dinner table. Something had to be holding them in place. The trouble was that this something did not behave like any familiar force. Gravity was far too weak at nuclear scales. Electromagnetism was strong, yes, but it was part of the problem, because positive protons repelled one another. The force inside the nucleus had to be much stronger than electric repulsion at very short distances, but it also had to fade almost completely outside the nucleus. It was a force with a very specific personality, powerful up close, nearly absent at a distance, like a door latch that grips firmly only when the door is exactly shut, and otherwise does nothing at all. This was the puzzle Hideki Yukawa stepped into. Yukawa was a Japanese physicist working at a time when the subatomic world was still opening. Today we're used to hearing about many particles, with names that sound as if nature had a large filing cabinet and very little concern for simplicity. But in Yukawa's time, the known particle list was much shorter. The electron was known, the proton was known, the neutron had recently joined the story. The photon was understood as the quantum of light. But the larger zoo of particles had not yet arrived. Suggesting a new one was not something to do casually, like adding another cushion to a sofa. It meant making a serious claim about what nature must contain. Yukawa's idea was bold because he did not start with a particle that had already been seen. He started with the behavior of a force. He asked, in effect, what kind of particle would need to exist in order for the nuclear force to act the way it does? If the force between protons and neutrons was carried by some exchanged particle, then the short range of that force could tell us something about the particle itself. A force that reached only a tiny distance suggested a carrier particle with mass, not a particle as heavy as a proton or neutron, not a particle as light as an electron, something in between. This was a remarkable piece of reasoning. It was like hearing a muffled sound through a wall and correctly guessing not only that there is a room behind it, but roughly how large that room must be. Yukawa could not point to the particle in his detector. He could not hold up a photograph and say, there it is. He inferred it. He listened to the shape of the problem and followed the logic. The nucleus had a force. The force had a range. The range suggested a mass. Therefore, a particle with that mass might be responsible for carrying the force between nucleons. The particle Yukawa predicted belonged to a middleweight category, heavier than the electron and lighter than the proton. This is where the name meson comes from, based on the idea of something intermediate. The specific particle later associated with Yukawa's nuclear force would become known as the Pion, or meson. At the time, though, it was a prediction, a missing piece drawn from theory before it was clearly identified in nature. It was not yet a familiar member of the particle family. It was more like a silhouette in the doorway. There is a calm lesson here about how science sometimes works. We often imagine discoveries as sudden moments of seeing. A telescope turns toward the sky, and a new moon appears. A microscope reveals a hidden cell. A detector records a track and a particle is found. But some discoveries begin before anything is seen. They begin as necessities. The mathematics, the measurements, and the contradictions quietly point towards something missing. The new thing is not guessed wildly. It is demanded by the pattern. Yukawa's particle was like that. The nucleus had left an empty chair at the table, and the theory suggested who should be sitting in it. The idea of exchange particles was still developing, but it was becoming a powerful way to think. Instead of imagining forces as simple, invisible pulls between objects, physicists were learning to describe interactions through fields and their associated particles. In electromagnetism, the photon played this role. Light itself was made of photons, and electromagnetic interactions could be described in terms of photon exchange. Yukawa applied a similar kind of thinking to the nuclear force, but with an important difference. The photon has no mass, and electromagnetism can reach across enormous distances. The nuclear force is short-ranged, so its messenger had to be massive. That single difference changed the whole character of the force. A massive messenger particle does not allow its force to stretch endlessly through space. Its influence drops away quickly. This matched the nuclear force beautifully. The protons and neutrons could bind when extremely close, but the force would not reach far beyond the nucleus. It would not affect everyday objects directly at human distances. It would remain hidden where it belonged, in the tiny, dense center of atoms. That is part of why the world can be stable without being welded into one enormous nuclear lump, which would be inconvenient for furniture, weather, and most social arrangements. Yukawa published his idea in the 1930s. At first, it was not immediately accepted as a complete solution, partly because the predicted particle had not yet been found, and partly because nuclear physics itself was still developing rapidly. The world of particles was not yet mapped clearly. Detectors were improving. Cosmic rays were being studied. Particle accelerators were still young. Scientists were learning how to read the faint signatures left by subatomic events. It was a time when theory and experiment were moving toward each other through fog, each hoping the other had remembered to bring a lamp. Then came a complication. A particle was discovered in cosmic rays that seemed at first to match Yukawa's prediction. It had a mass in the general middle range, heavier than an electron and lighter than a proton. For a while, many thought this might be the nuclear force particle Yukawa had described, but nature, as usual, had saved a small twist for later. This particle turned out not to interact strongly with nuclei in the way the predicted force carrier should. It passed through matter too easily. It behaved more like a heavy cousin of the electron than like the particle responsible for binding the nucleus. This particle became known as the muon. The muon caused confusion because it looked at first like the answer, but it was not the right answer. It was as if someone had ordered a missing puzzle piece, received a piece of roughly the right size and colour, and then discovered it belonged to a completely different puzzle, possibly one that had wandered in from another table. The muon was important, and it would become central to particle physics in its own way, but it was not Yukawa's nuclear messenger. One physicist famously wondered who ordered it, which is still one of the most relatable reactions in all of particle physics. The real Pion was identified later. Experiments involving cosmic rays and photographic emulsions revealed particles that behaved much more like the predicted mesons. These pions interacted strongly and had the right role in nuclear processes. Charged pions and neutral pions became part of the growing particle picture, and Yukawa's theoretical prediction was vindicated. The particle that had seemed necessary from the range of the nuclear force was not merely an elegant idea, nature had actually made it. This is one of the reasons Yukawa's work became so celebrated. He showed that the nuclear force could be understood through the exchange of a particle. He predicted the approximate mass of that particle from the force's short range, and when the Pion was finally identified, it confirmed the deep connection between force range and particle mass. It was not just a lucky guess, it was a successful act of theoretical physics, where careful reasoning reached into a hidden part of nature before experiment had fully lit the way. There is something almost restful about that if we let it be. The universe often seems overwhelmingly complicated, but sometimes its complications leave clues. The nucleus was difficult, but not silent. It showed its nature through stability, through short-range attraction, through the failure of known forces to explain it. Yukawa followed those clues and found the outline of a particle. He did not solve every mystery of the strong force, no one person did. But he gave physics a new way to speak about nuclear binding. He gave the hidden force a messenger. The Pion that emerged from this story was not a permanent part of ordinary matter in the same way protons, neutrons, and electrons are. It was short-lived. It appeared in high-energy processes, in cosmic ray interactions, in particle collisions, and in the theoretical description of nuclear forces. It could decay into other particles. It could be produced and vanish almost immediately. Yet its brief life did not make it unimportant. A match flame is brief too, but it can reveal the shape of a dark room. The Pion revealed something about the room inside the atom. In the exchange picture, protons and neutrons can interact by exchanging pions. This picture works especially well as an effective description of the nuclear force at distances relevant to nuclei. A proton and neutron do not simply sit like two beads connected by a visible spring. Their interaction is quantum. It involves fields, it involves possibilities and exchanges that cannot be pictured as tiny objects following neat paths in the ordinary sense. Still, the Pion gives the interaction a physical character. It allows physicists to say not only that the force exists, but also why it has the range it does and how it can connect nucleons. The charged pion is especially useful in imagining how protons and neutrons are related through the strong force. Since a charged pion carries electric charge, its exchange can change the charge state of the nucleon in simplified descriptions. A proton may become a neutron while emitting a charged pion, and another neutron may absorb it and become a proton, keeping the overall charge balanced. Again, this is a picture, not a little cartoon happening with visible balls inside the nucleus. But it captures an important truth. The nuclear force is not just attraction. It is a dynamic exchange that can involve the deep relationship between protons and neutrons. The neutral pion offers another piece of the story, helping describe interactions where charge does not change in the same way. It is extremely short-lived, even shorter-lived than the charged pions, and it decays quickly into photons. This behavior made it important in experimental particle physics, because its decay products could be detected and used to infer its presence. The Pion family, with its charged and neutral members, became a key part of understanding not only nuclear forces but also the broader world of particles produced in high-energy interactions. What Yukawa could not fully know at the time was that the Pion itself was not fundamental. Later, the quark model revealed that mesons are made of a quark and an antiquark. The Pion, therefore, is a composite particle. It is built from smaller constituents bound by the deeper, strong interaction. This might seem at first to reduce its importance, but it does not. It changes the level of explanation. The Pion remains vital because it is the lightest meson and plays a special role in the low-energy behavior of the strong force. It is part of how the deep quark and gluon world expresses itself at the level of protons and neutrons. This happens often in science. A thing can be not fundamental and still be essential. Water is not fundamental because it is made of molecules, and those molecules are made of atoms, and those atoms are made of smaller particles. But water still matters if you are thirsty, sailing, cooking pasta, or trying to understand weather. In the same way, the Pion is not fundamental in the deepest known sense, but it remains essential for understanding nuclear physics. It is one of the ways the strong interaction becomes visible at the scale of nuclei. Yukawa's prediction also changed how physicists thought about mass, force, and range. A particle's mass was not just a property sitting on a list. It could help determine how far a force reaches. The nuclear force was short-ranged because its effective messenger was massive. This gave a physical reason for the force's strange behaviour. The nucleus no longer had to be imagined as held together by a mysterious invisible cement. It could be understood as an arena of exchange, where pions played the role of short-range messengers between nucleons. It is worth pausing on the courage of the prediction itself. Theoretical physics often requires a kind of disciplined imagination. Too little imagination, and you never see beyond known facts. Too much, and you drift into ideas that cannot be tested or tied to evidence. Yukawa found a path between the two. He allowed himself to imagine a new particle, but he anchored it in the measured behaviour of the nuclear force. The new particle had a reason to exist. It had a job. It was not decoration. It was not there because the theory looked lonely. It was there because the nucleus would not make sense without something like it. And once the Pion was found, it helped open the door to a broader understanding of particle physics. The world was not made only of protons, neutrons, electrons and photons. There were mesons. There were muons. There were particles that appeared in cosmic rays and accelerators, some stable enough to study directly through their tracks, others so brief that they had to be reconstructed from what they became. The Pion was part of the beginning of the particle zoo, the growing realization that nature had many short-lived forms of matter, especially when high-energy processes revealed them. For the story of matter, though, the Pion's importance remains beautifully focused. It helped explain why the nucleus holds. It showed that the strong nuclear force between nucleons could be understood through particle exchange. It connected the short range of the force to the mass of the messenger. It gave a name and a form to something that had previously been only an inferred attraction. The particle that had to exist did exist, and with it, the hidden glue of matter became a little less hidden. This does not mean the Pion is a tiny lump of glue floating between protons and neutrons. That image is tempting, but too literal. The Pion is part of a quantum field description. In nuclear forces, it often appears as a virtual exchange, a feature of the interaction rather than a long-lived free particle inside the nucleus. When produced in collisions, it can exist as a real particle for a very short time before decaying. It has more than one role depending on the physical situation. That flexibility can be confusing, but it is also what makes it useful. The Pion is both a particle we can detect through its products and a powerful way to describe interactions we cannot see directly. Perhaps the simplest way to hold the idea is this. Yukawa looked at the nucleus and saw that a force was missing from the known story. He reasoned that this force could be carried by a particle. The force's short range told him the particle should have mass. Experiments later found the Pion matching the role his theory had suggested, and from that point on, the nucleus was no longer just a crowded cluster held by an unnamed power. It became a place of exchange, where protons and neutrons could be linked by brief messengers too small and too fast to see, but not too hidden to understand. That is the quiet drama of Yukawa's prediction. It was not dramatic in the noisy sense. No thunderclap, no glowing particle appearing under a glass dome. Just a careful mind following a difficult clue. A force with a short reach, a nucleus that should not hold together without help, a particle that had to exist if the picture was right. And then, years later, the tracks and decays and interactions that showed the Pion was really there. So now we have the main characters in place. The protons and neutrons crowded inside the nucleus. The strong force binding them at tiny distances. Yukawa's predicted messenger, the Pion, giving that force a physical shape. But to understand what it means for pions to carry the strong nuclear force, we need to move more slowly into the interaction itself, into the way a particle exchange can produce attraction, and why the pion became such a useful bridge between the stable world of nuclei and the deeper restless world of quarks and gluons. When we say that pions carry the strong nuclear force, we have to be a little careful, because nature has a fondness for giving us sentences that are useful before they are completely exact. The Pion does carry the force in an important sense, but not in the deepest possible sense. It is not the final carrier of the fundamental strong interaction between quarks. That deeper job belongs to gluons. The pion belongs more to the force between protons and neutrons, the leftover strong attraction that helps bind the nucleus together. It is the messenger of the nuclear force in the older and still very useful picture, the picture that helped physicists understand why nucleons stay close inside the tiny heart of the atom. This distinction matters, but it does not have to be rushed. Physics often has layers. At one layer, water is a liquid that flows, freezes, boils, and fills a cup quite nicely. At a deeper layer, water is made of molecules. Deeper still, those molecules are made of atoms. Deeper again, atoms are made of nuclei and electrons. And deeper still, nuclei are made of protons and neutrons are made of quarks and gluons. None of those descriptions makes the earlier ones useless. A sailor does not need to describe every molecule of the sea in order to understand waves. A cook does not need quantum theory to boil water, though it might make the pasta take longer if they insisted on explaining it first. In the same way, pions remain incredibly useful for describing the force between protons and neutrons, even though a deeper theory tells us that quarks and gluons are working underneath. So let us stay for a while at the level of the nucleus. Imagine two nucleons, perhaps a proton and a neutron, close together inside the atomic nucleus. They are not touching like little stones. They are quantum objects with fuzzy boundaries, inner structure, and fields around them. Still, they are near enough for the strong nuclear attraction to matter. At these distances, the pion can be thought of as the exchanged particle that allows one nucleon to influence the other. It is as though the proton and neutron are not simply sitting side by side, but are engaged in a rapid, invisible exchange that produces attraction. The word exchange is doing a great deal of work here. In everyday life, exchange usually means handing something over. You pass someone a note, you toss a ball. You lend a book and secretly hope it returns with the same spine it left with. But in quantum physics, an exchange particle is not always like an ordinary object travelling from one place to another in a neat little path. The process is more subtle. It is described through quantum fields, probabilities, and interactions. When a pion is exchanged between nucleons, it can be virtual, meaning it is part of the internal workings of the interaction, rather than a free particle that could be directly caught before and after the event. Virtual does not mean pretend. It does not mean unreal. It means the particle appears inside the calculation and the physical process as a temporary feature of the interaction. Its effects are real, even if it is not observed as a long-lived particle flying out of the nucleus. A gentle comparison is the way a conversation can change two people without any physical object remaining between them. Words are spoken, meaning passes, moods shift, decisions change, and then the sound is gone, the effect remains. Of course, pions are not words, and nucleons are not chatting in the candlelight, but the idea helps loosen us from the picture of force as a permanent string tied between objects. In quantum physics, force is often more like an ongoing transaction. The particles are changed by the exchange, and the exchange is the way the relationship happens. For protons and neutrons, the pion exchange picture explains the short-range nature of the nuclear force. A pion has mass. Because it has mass, the force associated with its exchange does not reach very far. It fades quickly beyond the size of the nucleus. This is why the strong nuclear force can hold nucleons together when they are close, but does not glue your left hand to a distant wall, or pull the moon into a giant nuclear embrace, which would be both spectacular and deeply unhelpful. The pion's mass gives the interaction a limited reach. The force is strong, but it is local. It works in the tiny room of the nucleus and not across the hallway of the universe. This short range gives the nucleus its special character. A proton feels the strong attraction mainly from nearby nucleons. It does not strongly attract every nucleon in a large nucleus equally across the whole space. That is different from electric repulsion, which can act over longer distances. In a heavy nucleus, all the protons repel one another through electromagnetism. while the strong force mainly helps among close neighbours. This is one reason very heavy nuclei become difficult to keep stable. The nuclear attraction has a short reach, but the electric repulsion keeps adding up. The nucleus is always a balance between closeness, charge, and binding. Pions help create that binding between nucleons. In a simplified picture, a proton can emit a pion and become a neutron, while a nearby neutron absorbs that pion and becomes a proton. The identities can swap in a way that preserves the total charge and keeps the nucleons connected through the strong interaction. This sounds almost like a magic trick if said too quickly. A proton becomes a neutron becomes a proton, a pion passes between them, but it is not magic. It reflects the deep relationship between these particles. Protons and neutrons are close relatives under the strong force. They are different partly because of their electric charge and the arrangement of their quarks, but the strong interaction treats them in a very similar way. There are charged pions and a neutral pion, and this small family allows different kinds of exchanges. A charged pion can be involved in interactions where the charge state of the nucleon changes. A neutral pion can be involved when the nucleons interact without changing charge in that same way. Together, the pions give the nuclear force a flexible vocabulary. They allow the attraction between protons and neutrons, and neutrons to be described in ways that match the observed behaviour of nuclei. Again, this is a picture held at the level of nuclear physics. It is powerful, but it is not the lowest layer of explanation. Underneath it, quarks and gluons are doing the deeper work. The deeper picture says that protons and neutrons are made of quarks, and that quarks are bound by gluons. The gluons carry the fundamental strong interaction. They are responsible for keeping quarks confined inside hadrons, a family of particles that includes protons, neutrons, and pions. In this deeper view, a pion is itself made from a quark and an antiquark. It is not elementary in the same way an electron appears to be. It has inner structure. It is a little packet of the strong interaction's own world, a composite particle born from the same deep force it helps express between nucleons. This can sound circular at first. The strong force makes pions, and pions help carry the strong force between nucleons. It is a bit like saying the sea makes waves, and waves carry the movement of the sea. But that is not really circular, it is layered. Gluons bind quarks inside protons, neutrons, and pions. Then pions as composite particles appear in the effective force between protons and neutrons. The pion is not the root of the strong force. It is one of the ways that root grows upward into the nuclear world. This is why physicists often call the force between nucleons a residual strong force. Residual does not mean weak or unimportant. It means it is a leftover effect of the deeper strong interaction inside the nucleons. A good comparison comes from molecules. Atoms can be electrically neutral overall, but they can still attract one another through leftover electromagnetic effects. Those effects allow molecules to form, liquids to behave as they do, and many materials to have their structure. In a somewhat similar spirit, protons and neutrons are colour neutral overall, but the strong interaction inside them leaves behind an effect that can bind them to other nucleons. Pion exchange is one of the main ways to describe this leftover attraction. The pion is especially important at longer distances within the nucleus scale. That phrase may sound odd because all nuclear distances are tiny to us, but even inside the nucleus, there are relatively shorter and relatively longer ranges. At the outer part of the nuclear force's reach, pion exchange is very important. It is like the gentlest long arm of a force that is still far too short to matter outside the atom. At shorter distances, other effects and other meson exchanges can become important, and the full nuclear force becomes more complicated. But the pion remains central because it is the lightest meson, and lighter exchange particles have a longer reach than heavier ones. So within the tiny scale of the nucleus, the pion is the messenger that can reach furthest. That last idea is worth resting on. In the human world, a light messenger might travel faster or easier across a field. In the quantum world, the mass of the exchange particle helps determine how far the associated force reaches. The pion is not massless, so its reach is still limited. But because it is relatively light compared with many other strongly interacting particles, it can help explain the longest range part of the nuclear attraction. It is the small bridge between nucleons, short by every ordinary standard, but long enough to matter deeply at the centre of the atom. This is one reason the pion became such a beautiful answer to Yukawa's problem. The nuclear force had to be short-ranged. The pion had the right kind of mass to make that possible. The force had to be strong enough to bind protons and neutrons. Pion exchange provided a way to describe that attraction. The force had to treat protons and neutrons as closely related. The pion's charged and neutral forms fit naturally into that relationship. The particle had to be too elusive to see directly inside ordinary matter, but able to leave evidence in high-energy processes. The pion did just that. It was not simply a particle that happened to exist. It was a particle whose properties matched the job the nucleus required. Of course, the nucleus is not merely two particles exchanging one pion. Real nuclei can contain many nucleons, all interacting at once. The quantum state of a nucleus is a collective arrangement. Each nucleon feels the presence of others. The pions in the effective description are not lined up like little workers carrying buckets between fixed locations. The interactions overlap, combine, interfere, and depend on the full nuclear environment. That makes nuclear physics difficult, but also rich. A nucleus is more like a tightly coordinated storm than a stack of parts. The pion is one of the important patterns in that storm. When physicists build models of nuclear forces, pion exchange often appears as the starting point for the long-range part of the force. Then additional terms are added to account for shorter-range behaviour. This is because the nuclear force has a shape. At certain distances it is attractive. At extremely short distances it can become strongly repulsive, preventing nucleons from simply collapsing into one another. This repulsive core is part of why nuclei have structure and density rather than shrinking without limit. The attraction holds nucleons together, but the repulsion at very short distances prevents them from all occupying the same tiny point. Matter, once again, is balance. The pion contributes to the attractive part, especially across the nuclear distances where the force needs to bind but not crush. If the force were only attractive with no limit, nuclei would behave very differently. If it were only repulsive, they would not bind. The actual nuclear force is subtle. It depends on distance, spin, charge, and other quantum properties. It is not a simple pull like a rope. It is more like a set of rules that changes depending on how the particles are arranged. Pions help write some of those rules. Spin also plays a role in nuclear forces, though we can keep it light here. Protons and neutrons have quantum spin, a built-in angular momentum that is not the same as a little ball physically rotating. The pion exchange force depends partly on how these spins are arranged. This helps explain why some combinations of nucleons bind and others do not. For example, a proton and neutron can form a stable pair known as the deuteron, the nucleus of heavy hydrogen. But two protons alone do not form a stable bound nucleus in the same way, partly because of electric repulsion and the details of the nuclear force. The pion exchange picture helps describe these differences, though the full calculation is more complex than a bedtime script should be expected to carry on its back. The deuteron is a useful example because it is the simplest bound nucleus with more than one nucleon, one proton and one neutron, just two particles, held together by the nuclear force. It is not bound very tightly compared with many larger nuclei, but it is stable. In studying the deuteron, physicists learned a great deal about the force between nucleons. Pion exchange helps explain important features of that force, including how it depends on spin and orientation. So even the simplest nuclear pair contains deep information about the pion's role. But pions do not only exist in theory. Real pions can be created when particles collide with enough energy. In cosmic ray showers, high-energy particles from space strike atoms in the atmosphere and produce pions among other particles. In particle accelerators, collisions produce pions in large numbers. Charged pions decay into muons and neutrinos. Neutral pions decay into photons. These decay patterns allow scientists to identify them. The pion is too small and brief to see directly, but it leaves signatures like a guest who has vanished from a room but left behind a warm cup, a moved chair, and perhaps a faint sense that something interesting just happened. Those real pions and the virtual pions of nuclear force calculations are related, but they appear in different contexts. A real pion is produced as an outgoing particle in a collision and can be detected through its decay products. A virtual pion is part of an internal interaction between nucleons. The same kind of particle is involved, but its role differs depending on the process. This distinction can feel slippery because ordinary experience does not prepare us for particles that can be both detectable objects and internal features of interactions. But quantum theory is comfortable with that kind of dual role. The world at small scales is not obliged to behave like a drawer of labelled marbles. The Pion also reminds us that forces are not always explained by simple contact. In everyday life, contact feels basic. One thing touches another, and motion changes. But at smaller scales, even contact becomes a complicated idea. Atoms do not truly touch like solid billiard balls. Electromagnetic fields repel electron clouds. Quantum rules shape the arrangement. Inside the nucleus, nucleons interact through fields and exchanges. What we call touching is usually a large-scale impression created by forces. Matter resists matter not because tiny surfaces are literally hard in a familiar way, but because underlying fields and quantum rules produce resistance. The Pion belongs to the same deep lesson. Forces make the world feel solid, not the other way around. This is why the phrase "the particle that holds matter together" is both meaningful and simplified. The Pion does not hold all matter together by itself. Electromagnetism holds atoms and molecules into ordinary materials. Gluons hold quarks inside protons and neutrons. Gravity holds planets and stars together. But the Pion helps explain the binding between protons and neutrons in atomic nuclei. And without stable nuclei, matter as we know it would not exist. So the Pion is not the only glue. It is one important form of hidden nuclear glue, one of the first messengers that showed how the strong force could create stable atomic centers. It is little like asking what holds a house together. You might say nails, but also beams, screws, foundations, gravity, wood fibers, and the patience of whoever built it. Each answer is true at a different level. For matter, the answers also come in levels. Electrons and nuclei are held into atoms by electromagnetism and quantum structure. Nucleons are held into nuclei by the residual strong force. Quarks are held into nucleons by gluons. Pions are central to the effective force between nucleons. They are not the whole house, but they are part of the framework without which the house would not stand. One of the reasons the Pion story is so satisfying is that it connects the invisible with the measurable. The force inside the nucleus cannot be seen directly. The exchange of virtual pions cannot be filmed, but the theory predicts behavior and experiments confirm patterns. Nuclear scattering, bound states, particle production, and pion decay all fit into the wider picture. The pion is not merely a poetic idea. It has mass, charge states, lifetimes, decay modes, and interactions that can be studied. It is one of those places where the invisible world becomes precise. And still, even with precision, there is room for wonder. A particle made from a quark and an antiquark can appear as the messenger of attraction between nucleons, which themselves are made of quarks. A brief exchange can help create long-lasting stability. A short-range force can support the entire periodic table. A tiny interaction inside the nucleus can eventually help make stars, planets, oceans, and sleeping rooms. Physics does not remove wonder by explaining things. It changes the address of wonder. It moves it from the surface of things into the workings beneath them. So how do pions carry the strong nuclear force? Gently stated, they carry the residual strong force between protons and neutrons by acting as exchange particles in the quantum description of nuclear interactions. Their mass explains why the force is short-ranged. Their charged and neutral forms help describe different interactions among nucleons. Their connection to quarks and gluons ties the older nuclear picture to the deeper theory of the strong interaction. And their fleeting lives, whether virtual inside interactions or real in high-energy events, reveal that stability at our scale can be built from processes that barely last at all. That is the quiet centre of this part of the story. The nucleus is not held together by a static substance. It is held together by a dynamic force. The Pion helped give that force a face, or at least a very tiny temporary calling card. It showed that the attraction between protons and neutrons could be understood through exchange, and that exchange could be tied to a particle with just the right properties. The strong force inside the nucleus stopped being merely strange and began to become describable. And once physicists had this idea, they still needed nature to answer. A prediction is powerful, but it must eventually meet evidence. The Pion had to leave tracks somewhere. It had to appear in the world not only as a theoretical necessity, but as a detectable particle, however brief and elusive. The next part of the story moves from the inside of the nucleus to the rain of particles from space, where cosmic rays struck Earth's atmosphere and quietly wrote the Pion signature in trails, plates, chambers, and the careful records of people trying to read the invisible. For a long time, the Pion lived first as an idea. It was a missing shape in the theory of the nucleus, a particle suggested by the short reach of the nuclear force, a messenger that seemed almost required if protons and neutrons were to remain bound together. But physics cannot live on elegant ideas alone, no matter how nicely they fit into the furniture of the mind. At some point, the universe has to answer. A predicted particle must leave a mark. It must disturb something, decay into something, curve through a field, darken a photographic plate, or whisper its presence through the traces it leaves behind. The difficulty, of course, was that pions are not the kind of things one can simply place on a table and examine after dinner. They are short-lived. They are tiny beyond the reach of ordinary sight. They do not sit still for portraits. You cannot shine a desk lamp on a pion and say, "There you are, looking rather small today." Instead, the pion had to be found through evidence, through tracks and transformations, through the patient reading of particle footprints. And in the early 20th century, one of the richest sources of such footprints did not come from machines built on Earth, but from the sky. Cosmic rays were nature's particle accelerators long before humans built their own. High above our heads, energetic particles from space rush into Earth's atmosphere. Many of them are protons or atomic nuclei travelling at enormous speeds, launched by violent astrophysical processes such as exploding stars, active galaxies, or other extreme cosmic engines. When these particles strike atoms in the upper atmosphere, they create showers of secondary particles. One particle hits, and from that collision comes a cascade. New particles are born, decay, collide, and transform, raining downward in a silent, invisible storm. We walk through this storm every day without noticing. It passes through the air, through buildings, through our bodies, through mountains, and through the quiet spaces between one thought and the next. To early physicists, cosmic rays were both a gift and a nuisance. A gift, because they reached energies that laboratory equipment could not yet produce. A nuisance, because they arrived when and where they pleased, without filling out a schedule or responding to polite requests. Studying cosmic rays was a little like trying to study rare birds by standing in a field with a notebook and hoping one landed nearby. You could improve your chances by choosing better locations, higher mountains, balloons, deep mines, clever detectors, but you still had to wait for nature to send the event your way. Yet cosmic rays revealed new particles before accelerators became powerful enough to do the same. They were part of the story of the positron, the muon, and eventually the pion. They made the sky into a laboratory, with Earth's atmosphere acting as both target and filter. The particles produced in those high-altitude collisions carried clues about the hidden laws of matter. All physicists had to do was find a way to read them. Reading them required detectors. Not detectors in the modern sense of giant electronic systems with millions of channels and rooms full of computers, but beautifully physical instruments that made invisible particles visible through their effects. Cloud chambers, for example, allowed charged particles to leave trails in supersaturated vapor. When a charged particle passed through, it ionized the gas along its path, and droplets formed around those ions, leaving a thin, cloudy track. It was like watching a tiny airplane write a line across the sky, except the airplane was subatomic and the sky was inside a chamber on a laboratory bench. Bubble chambers came later and worked with a related kind of beauty. A charged particle passing through a superheated liquid would leave a trail of bubbles. Magnetic fields could curve the tracks, helping physicists infer the charge and momentum of the particle. Photographic emulsions were another powerful tool. Special plates thick with sensitive material could record the tracks of charged particles as tiny darkened paths. After exposure, the plates were developed and examined under microscopes. To the untrained eye, the images might look like scratches, threads, or accidental marks. To skilled observers, they were messages from the subatomic world. There is something wonderfully humble about this. The discovery of deep particles often depended on people staring carefully at small marks, not at glowing orbs, not at dramatic flashes, not at particles waving from inside the atom, just tracks, curves, breaks, little forks where one particle became another. The universe left handwriting in the detector, and physicists learned to read it. Before the pion was clearly identified, another particle caused a great deal of confusion. In the 1930s, cosmic ray studies revealed a particle with a mass between that of the electron and the proton. This seemed at first like a possible match for Yukawa's predicted meson. After all, Yukawa had expected something intermediate, heavier than an electron and lighter than a proton. Here was such a particle, falling from the sky in cosmic ray events. For a moment it looked as if the missing nuclear messenger had arrived. But the particle did not behave correctly. The supposed nuclear force carrier should have interacted strongly with atomic nuclei. It should have been eager to participate in nuclear processes. Instead, this new particle passed through matter too easily. It seemed strangely indifferent to the strong force. It was not binding nuclei. It was not the messenger Yukawa had predicted. It was later understood as the muon, a heavier relative of the electron important in its own right, but not the answer to the nuclear force puzzle. The muon had walked onto the stage wearing a costume that briefly resembled the Pions, then calmly revealed it was in the wrong play. This confusion was not a failure. It was part of the process. Nature often answers one question by handing over a different question first. The muon itself became a major discovery, a sign that the particle world was richer than anyone had expected. But it left Yukawa's predicted nuclear meson still missing. The force inside the nucleus still needed its messenger. The empty chair remained empty. The true charged pion was identified later through careful work with photographic emulsions exposed to cosmic rays, especially at high altitudes where the particle showers were stronger. In the 1940s, researchers including Cecil Powell, Giuseppe Occhialini, and Cesar Lattes helped reveal the pion's tracks in these emulsions. The technique was patient and demanding. Plates had to be prepared, carried to high places or exposed under suitable conditions, developed, and then searched under microscopes for the tiny patterns that would show one particle decaying into another. The key evidence came from events where a heavier particle decayed into a muon. This was exactly the kind of signature that helped distinguish the pion from the muon. A charged pion could come to rest in the emulsion and then decay into a muon, which would travel a short distance before decaying further. The pattern had a recognizable sequence. One track ended, another began, and from this little kink in the microscopic record, a new particle became real to science. It is hard to imagine a quieter discovery of something so important. No explosion, no thunder, just a track in an emulsion plate, a tiny path left by a particle that had already vanished. There is a lovely contrast here between scale and meaning. The mark was small enough to require a microscope and expertise. The particle lived briefly enough to make everyday time seem absurdly slow, and yet the meaning of the discovery reached into the heart of matter. It confirmed that the particle Yukawa had predicted was not just a mathematical convenience. There really was a meson with the right kind of behaviour to be connected with the nuclear force. The Pion had stepped out of theory and into evidence, though even stepping out is too slow a phrase for something so brief. The charged Pion was not the only member of the family. The neutral Pion was identified as well, though it left different kinds of evidence because it decays extremely quickly into photons. It does not leave a long charge track in the same way because it carries no electric charge overall. Instead, its presence is inferred from the electromagnetic showers or photon signatures produced by its decay. This made it harder in some ways to catch, but once the charged and neutral Pions were established, the Pion family made far more sense. The theory had expected related particles with different charges, and nature provided them. The discovery of the Pion was also a turning point in how physicists understood particles produced by cosmic rays. The sky was not merely sending known particles down to Earth, it was creating new ones through high-energy collisions. This meant that particle physics would need to become a study not only of stable matter, but of unstable particles, decay chains, and transformations. The world of matter was not limited to the particles that survive long enough to build atoms. There were brief particles too, particles that appeared in violent conditions and vanished quickly, but whose properties revealed the laws underneath. This was the beginning of a crowded era. More particles would be discovered. Kaons, hyperons, resonances, and many others would join the growing list. For a while, the particle world seemed almost embarrassingly full, as if nature had opened a drawer and found that it had been keeping spare particles in there for no obvious reason. Physicists eventually called it the particle zoo, partly with affection, and partly, one suspects, with the tired expression of people whose tidy theories had become overrun by new species. But the Pion was among the early and essential members of this expanding world. It was not a random animal in the zoo. It had a clear theoretical role from the beginning. The cosmic ray method also shows us how discovery depends on environment. At sea level, many particles produced in the upper atmosphere decay or are absorbed before reaching detectors. Higher altitudes offered better chances. Mountains became laboratories. Balloons carried instruments upward. Later, accelerators would take over much of the work, creating controlled beams and collisions on demand. But before that, scientists relied on the universe itself to provide high-energy events. The heavens, in a very literal way, helped reveal the particle that helps explain the nucleus. There is something pleasing in that connection. The Pion helps hold together the tiny centres of atoms, and it was discovered partly through particles arriving from vast cosmic distances. The smaller scale and the larger scale met in a photographic plate. A cosmic ray struck the atmosphere, produced a shower, a Pion left a track, and a human eye later studied that mark under a microscope. The story stretches from outer space to nuclear space, from violent astrophysical sources to the quiet labour of looking carefully. Physics is full of these strange bridges. Once Pions could be produced and studied in laboratories, their properties became clearer. Particle accelerators allowed physicists to create pions more reliably than waiting for cosmic rays. They could measure pion masses, lifetimes, charges, decay products, and interactions. They could scatter pions from protons and nuclei. They could test theories of the nuclear force. The Pion changed from a rare visitor from the sky into a regular subject of experimental study. It became part of the working language of particle and nuclear physics. The charged pions were seen to decay mainly into muons and neutrinos. The neutral Pion decayed into photons. These decays connected the Pion not only to the strong interaction, but also to the weak and electromagnetic processes involved in its transformation. A Pion may be born through the strong interaction and decay through another. This is one of the strange social habits of particles. Their creation and decay do not always belong to the same force. A particle can enter by one door and leave by another, and by watching both doors, physicists learn about the building. The Pion's short lifetime also helped confirm that it was not an ordinary constituent of stable matter. Protons, neutrons inside stable nuclei, and electrons make up atoms because they can persist. Pions do not persist in that way. They are produced in special conditions and then decay. But their short lives do not prevent them from playing a role in nuclear forces as virtual exchange particles. This is one of the subtle distinctions that the Pion asks us to hold. A free pion is fleeting. A virtual pion in the nuclear interaction is part of the binding description. The same particle type appears differently depending on context. The world is not always one label per thing. Photographic emulsions themselves deserve a little appreciation here. They were not glamorous in the modern electronic sense, but they were extraordinarily sensitive. A charged particle passing through could leave a trail of changed grains in the emulsion. After development, the track could be measured. The thickness, length, curvature, and decay pattern could reveal the identity and behavior of the particle. It was slow work. It demanded attention. Before computers could sift through enormous data sets, human observers spent hours examining plates, following tiny lines through magnified fields. There is almost a meditative quality to it, though perhaps less relaxing after the 1000th track. Those early tracks did more than identify one particle. They helped build confidence in the whole exchange picture of nuclear forces. If the Pion existed and had the expected properties, then Yukawa's idea had captured something real. It did not mean every detail of nuclear force was solved, but it meant the central insight was sound. The short-range nuclear force could be tied to a massive meson. The binding of protons and neutrons could be studied through particle exchange. Theory and experiment had met, not perfectly, but enough to change the map. It is important, though, not to make the discovery sound too neat. Science rarely moves in a straight line from prediction to confirmation, with everyone smiling and nodding in matching lab coats. There were mistaken identifications, confusing particles, debates over interpretation, and technical challenges in detection. The muon complicated the story. The Pion had to be separated from other cosmic ray products. The equipment had limits. The events were rare and delicate, but this messiness is part of why the discovery is trustworthy. It was not accepted because it was convenient. It had to survive confusion, comparison, and repeated evidence. The Pion's discovery also helped mark a transition from nuclear physics into modern particle physics. The nucleus was no longer merely a place where protons and neutrons sat together. It was connected to a broader world of mesons, leptons, decay processes, and high-energy interactions. The question of what holds matter together opened into the question of what particles exist at all, why they have their properties, and how they transform. The Pion stood near that doorway. It belonged to the nucleus, but it also belonged to the expanding particle zoo and eventually to the quark model that would explain mesons as quark-antiquark pairs. For the listener, perhaps the most useful image is not a diagram but a trace. A tiny path in a detector. A particle appears, slows, stops, decays. Another track begins. The Pion is no longer only a need in an equation or a proposed messenger between nucleons. It has left a mark. It has touched the material of the detector and changed it. Its brief existence has become visible through consequence. That is often how hidden reality becomes known, not by stepping fully into view, but by changing something that can be seen, and there is a certain tenderness in that, if we can use such a word carefully around particle physics. The Pion does not last long, but it leaves evidence. It does not become part of ordinary matter for long, but it helps explain why ordinary matter can exist. It is born in energetic collisions, in the atmosphere or in accelerators, and then almost immediately becomes something else. Yet in that short interval, it tells us about the force that binds the atomic nucleus. It is brief, but informative. A quick note passed from nature to anyone patient enough to read the handwriting. So the first glimpse of the pion was not a glimpse in the ordinary sense. No eye saw the particle directly. No lens formed an image of it. What physicists saw were trails, decays, patterns, and the agreement between those patterns and the particle Yukawa's theory had expected. The pion appeared as evidence, and evidence is how much of the invisible universe becomes real to us. It appeared in cosmic rays, in emulsions, in the careful study of tracks, in the distinction between the muon that was not the answer and the pion that was. From the sky came the clues, from the microscope came the reading, from the theory came the question, and from the nucleus came the need. Now that the pion had been predicted and found, the story could go deeper again. The particle that helped explain the force between protons and neutrons was itself not simple. It had structure. It belonged to a family. It was made from quarks, tied to gluons, and connected to the deeper machinery of the strong interaction. The messenger of nuclear binding turned out to be a message about a still more hidden world, where even protons and neutrons are not the final bricks, and the matter we trust begins to look less like solid pieces and more like patterns woven from fields, symmetries, and restless inner motion. By the time the pion had been predicted, confused with the muon, finally identified, and placed into the story of the nuclear force, it had already earned its place as one of the great clues in 20th century physics. It helped explain how protons and neutrons could feel a strong attraction across the tiny distances inside the nucleus. It gave Yukawa's idea a real particle to stand on. It turned the nucleus from a mysterious tight bundle into a place of exchange, where hidden messengers helped matter stay bound. But as often happens in physics, the answer did not stop the questioning. It only moved the mystery one level deeper. Because if the pion helps explain the force between protons and neutrons, then we have to ask a quieter but more demanding question. What is the pion itself made of? At first, this might sound like asking what a shadow is made of, or what a note in a song is made of. The pion was already small, already brief, already difficult to detect directly. Surely one might think it must be near the bottom of things. But the history of physics has a habit of making the bottom move. Atoms were once thought to be indivisible, then the electron appeared. The nucleus was found. Protons and neutrons arrived. For a while, protons and neutrons seemed like basic pieces of matter, heavy little residents of the nucleus, dependable and solid in the way a particle can be solid, which is to say, not very solid at all. Then physicists discovered that even they had inner structure. This deeper story leads us to quarks. Quarks are among the fundamental building blocks in the modern picture of particle physics. They are not found alone in ordinary conditions. You do not get a single loose quark drifting through the room, looking for somewhere to sit. They are always bound inside larger particles called hadrons. Protons and neutrons are hadrons. Pions are also hadrons. More specifically, protons and neutrons belong to a group called baryons, which are made from 3 quarks. Pions belong to a group called mesons, which are made from a quark and an antiquark. That one sentence opens a surprisingly large door. A quark and an antiquark. That is what a pion is in the modern picture. Not a tiny indivisible bead, not a little speck of nuclear glue, but a bound pair of deeper particles held together by the strong interaction. The positively charged pion can be described as an up quark paired with a down antiquark. The negatively charged pion can be described as a down quark paired with an up antiquark. The neutral pion is a more subtle mixture involving up and down quark combinations. We do not need to turn this into a memorization exercise because bedtime is not improved by sudden exams. The important point is simpler. The pion is composite. It has structure. It is built from quarks, and its existence belongs to the deeper machinery of the strong force. The word antiquark may sound like something from a very specialized fairy tale, but it simply means the antimatter counterpart of a quark. Many particles have antiparticles. partners with related properties but opposite charges in certain ways. When a quark and antiquark bind together, they form a meson. The pion is the lightest of these mesons, and that lightness is one reason it plays such an important role in nuclear physics. Among the particles made from quarks, pions are unusually easy for nature to produce in high-energy interactions, and they are especially important in the long-range part of the force between nucleons. But if quarks make pions, and pions help carry the force between protons and neutrons, what holds the quarks together inside the pion? That is where gluons enter the story. Gluons are the particles associated with the fundamental strong interaction. Their name is wonderfully direct. They glue quarks together, though again we must be careful with the image. They are not sticky droplets. They are not microscopic blobs of paste. They are force-carrying particles in the theory known as quantum chromodynamics, the modern theory of the strong interaction. The word chromodynamic sounds as if it has something to do with colour, and in a way it does, but not ordinary colour. Quarks carry a property called colour charge. This has nothing to do with red apples, blue blankets, or green tea. It is a label for a deeper kind of charge, one that determines how quarks interact through the strong force. The names red, green and blue are used for the types of colour charge, but they are only labels. A quark is not literally red in the way a painted door is red. No tiny blue quark is glowing inside the proton like a decorative light. The colour language is a mathematical tool, but a useful one. The rules of colour charge explain how quarks combine into particles that are colour neutral overall. Protons, neutrons and pions all hide their colour charge in balanced combinations, so they can exist as stable or briefly stable particles in the world we observe. This brings us to one of the strangest features of the strong interaction. Quarks are confined. They do not appear alone. Try to pull one quark away from another, and instead of separating cleanly, the energy you add can create new quark and antiquark pairs. It is as if pulling on the connection does not give you one loose quark, but instead creates more particles. A simple everyday comparison would be a string that, when stretched too hard, snaps into two new strings rather than giving you a free end. But even that picture is only a hint. The strong force behaves in a way that has no perfect daily life equivalent, which is why particle physics has to build its own language. Confinement explains why the world is not full of isolated quarks. We see protons, neutrons, pions and other hadrons, but not single quarks wandering independently. The strong force becomes stronger in a certain sense as quarks are pulled apart, unlike electromagnetism, which weakens with distance. This is part of what makes the strong interaction so strange and so powerful. It binds quarks into composite particles so tightly that the composites become the objects we can study directly. Inside a proton, 3 quarks are bound by gluons. But that simple 3-quark phrase hides a much livelier reality. A proton is not just 3 quarks sitting quietly in a triangle. It is filled with gluons and temporary quark-antiquark pairs, a restless sea of activity. Most of the mass of a proton does not come from the bare masses of its quarks. It comes from the energy of the strong interaction itself, from the motion and fields inside the proton. This is one of the most surprising lessons of modern physics. The mass of ordinary matter is not simply the sum of little hard pieces. Much of it is energy bound into stable patterns by the strong force. That means the matter around you, the chair, the floor, the cup, the hands resting quietly near you, owes most of its mass to the restless internal energy of protons and neutrons. The visible world is heavy because the invisible strong force is busy. If that does not make the room feel slightly stranger, it probably should. The solid objects around you are not solid because they are made of tiny solid things all the way down. They are solid because fields, forces and quantum rules create stable structures across many layers. The pion fits into this machinery as both a particle made by the strong force and a messenger of its leftover effects. It is made of a quark and an antiquark held together by gluons. Then, at the level of nuclear physics, pions can be exchanged between protons and neutrons, helping describe the residual strong force that binds nucleons together. In other words, the pion is born from the same deep interaction that it helps express. That may sound circular, but it is better understood as layered. Gluons hold quarks inside pions, protons and neutrons. Pions then help mediate the force between protons and neutrons. The deeper strong force creates the messenger that carries its echo between larger particles. A useful analogy, held gently, is the way molecules can create the properties of materials, and then those materials can influence other molecules. Water molecules create the liquid we call water, but water as a liquid can carry waves, dissolve salt, erode stone, or lift a boat. The molecules make the liquid, and the liquid then has behaviours that matter at a larger scale. In the same way, quarks and gluons create pions, and pions have behaviours that matter at the nuclear scale. The smaller level gives rise to the larger level, and the larger level has its own useful rules. The pion is also special because it is so light compared with many other particles made from quarks. This lightness is not an accident. It is connected to deep symmetry features of the strong interaction, especially a kind of symmetry involving the light quarks. We do not need to wander too far into that mathematical forest, because the trees have names that are not especially restful. But the gentle version is this. The strong interaction has patterns that would make certain particles very light if the light quarks had no mass. Since the up and down quarks do have small masses, the pions are not massless, but they remain unusually light. This makes them the longest range messengers of the residual strong force between nucleons. So the pion's lightness explains its reach. Not a reach across the room, not a reach across space, but a reach within the tiny world of the nucleus. Heavier mesons can contribute to nuclear forces at shorter distances, but pions dominate the longest range part of the nuclear attraction. They are like the outermost whisper of the strong interaction, still extremely short range by human standards, but long enough within the nucleus to help protons and neutrons feel one another. This is why pions remain useful even after the quark model. When physicists developed the idea that hadrons are made of quarks, they did not simply throw away pion exchange and start from scratch. The pion still worked, it still described important nuclear behaviour. The deeper theory explained why pions exist and why they have their properties, but it did not make them irrelevant, it gave them roots. The quark model itself was a response to the growing particle zoo. By the middle of the 20th century, physicists were discovering many hadrons, far more than expected. There were mesons, baryons, strange particles, resonances, and increasingly complicated families. It was beginning to look as if nature had more fundamental particles than anyone knew what to do with. The situation was a little like opening a kitchen drawer for a spoon and finding 100 unfamiliar utensils, each with a label, none of which seemed to match the soup. The quark model brought order. It suggested that many of these particles were not fundamental after all, but combinations of a smaller set of quarks. In that new order, the pion found its place as a meson made from the lightest quarks and antiquarks. Protons and neutrons found their place as baryons made from 3 quarks. The messy particle zoo began to look more like a periodic table of hadrons built from underlying components. The pion, once a mysterious nuclear messenger, became part of a wider family portrait, but the strong force still refused to become simple. Unlike electromagnetism, where photons do not carry electric charge, gluons themselves carry colour charge. This means gluons interact with other gluons. The force carriers are not passive messengers. They also feel the force they carry. This self-interaction makes the strong force highly complex. It is part of why quantum chromodynamics is mathematically difficult, and why understanding protons, neutrons, and nuclei from first principles remains one of the great challenges in physics. The strong force is not just strong, it is deeply entangled with itself. This self-interaction also helps explain confinement and the rich structure of hadrons. Gluons create fields that bind quarks, But because gluons interact with gluons, the field becomes complicated in a way that cannot always be pictured simply. A proton is not three quarks tied together by three neat strings. It is a quantum system full of interacting fields. A pion, though simpler in its basic quark, antiquark makeup, is also a strong force object with inner structure and dynamics. Even the simplest meson is not truly simple, and yet the pion has a kind of elegance. It is light, it is brief, it is made of a quark and an antiquark. It helps mediate the nuclear attraction. It appears abundantly in high-energy particle collisions. It decays in recognizable ways. It connects nuclear physics, particle physics, and the deep theory of the strong interaction. It is a small particle that sits at a crossroads. The charged pions decay mostly into muons and neutrinos through the weak interaction. The neutral pion decays into photons through the electromagnetic interaction. So even in their decay, pions connect different forces. They are made and interact strongly, but they can vanish through weak or electromagnetic processes. A pion's life is short, but it is socially connected in the particle sense. It passes through different parts of the standard model's machinery before disappearing into other forms. The idea that particles can transform is one of the biggest differences between modern physics and older pictures of matter. In everyday life, objects usually keep their identity unless something obvious happens. A cup remains a cup until it breaks. A book remains a book until someone spills tea on it, which is a tragedy of a small but serious kind. But particles can be created and destroyed. One particle can decay into others. Energy can become matter, and matter can become other matter. The pion is part of this world of transformation. It is not a permanent brick. It is more like a short-lived pattern allowed by the rules of fields. This does not make it less real. A wave on water is real even if it passes. A sound is real even if it fades. A candle flame is real even if it lasts only a moment. In physics, stability is not the only measure of reality. Short-lived particles are real because they have measurable properties and effects. They leave tracks. They decay in predictable ways. They interact with other particles. The pion is real in exactly this sense. Brief but definite. The deeper machinery of matter, then, is not a set of tiny permanent objects stacked inside one another forever. It is a hierarchy of fields and interactions. Electrons appear fundamental in the current standard model. Quarks appear fundamental. Gluons carry the strong interaction. Protons, neutrons, and pions are composite particles built from quarks and gluons. Nuclei are bound states of protons and neutrons. Atoms are nuclei with electrons around them. Molecules are atoms joined through electromagnetic interactions. Matter at our scale is the calm surface of many layers of hidden activity. The pion helps us travel between these layers. It is not as familiar as the proton, because it does not sit inside ordinary atoms as a stable resident. It is not as fundamental as the quark, because it is made from smaller pieces. It is not the deepest force carrier like the gluon, but it carries the residual strong force between nucleons in a very useful description. It belongs between levels. That is part of its importance. It is a bridge particle, a particle that tells us how one layer of physics emerges from another. And bridges are often where understanding happens. If you only study quarks and gluons, the nucleus can feel far away and impossibly complicated. If you only study protons and neutrons, the deeper strong force stays hidden. The pion lets us connect the two. It says that the strong interaction inside hadrons has consequences outside them. It says that the quark world is not sealed away from nuclear physics. It leaks out, not as loose colour charge, but as mesons, as residual forces, as the attraction that binds nuclei. The pion is one of the ways the hidden machinery reaches upward. This is why a full answer to what a pion really is must have more than one layer. It is a meson. It is made of a quark and an antiquark. It is a hadron, meaning it participates in the strong interaction. It is short-lived when produced as a free particle. It appears in charged and neutral forms. It helps describe the force between protons and neutrons. It is connected to deep symmetries of the strong interaction. It is not the fundamental glue itself, but it is a vital expression of that glue at the nuclear scale. It is small, brief, and yet woven into the reason matter can be stable. There is something quietly satisfying about this layered answer. The Pion is not one simple thing, because matter is not one simple story. At every depth, the world changes its language. At the human scale, we speak of objects. At the chemical scale, we speak of atoms and bonds. At the nuclear scale, we speak of protons, neutrons, and binding energy. At the particle scale, we speak of quarks, gluons, fields, and symmetries. The Pion is one of the words that carries meaning between those languages. So when we imagine the Pion now, we should not picture a tiny bead flying obediently between two solid balls. That picture helped us begin, but the deeper view is richer. A Pion is a quantum excitation, a meson made from quark and antiquark structure, born from the strong force, able to act as the messenger of the leftover strong interaction between nucleons. It is not a little object in the old-fashioned sense. It is a pattern in the fields of nature, a brief arrangement of deeper components, a messenger that is itself a message from the quark world. And that brings us closer to the heart of the whole question. What a Pion really is cannot be answered only by naming its parts. We could say quark and antiquark, and that would be true. We could say meson, and that would be true. We could say nuclear force messenger, and that would also be true in the effective picture. But the full meaning is found in how these truths fit together. The Pion is a particle that reveals relationship. It shows how protons and neutrons bind. It shows how quarks and gluons express themselves beyond individual hadrons. It shows how short-lived particles can support long-lived structures. It shows that matter is not built from stillness, but from interaction all the way down. The room around you may feel quiet now. The walls are not shaking. The air is not glowing with particle tracks. The objects nearby are not announcing their quark content, which is probably polite of them. But beneath that ordinary quiet, matter is held by layers of force. Electrons are arranged around nuclei. Nuclei are built from nucleons. Nucleons are built from quarks and gluons. Between nucleons, the Pion helps describe the attraction that keeps the centre of the atom bound. The deeper machinery is active, but its activity gives rise to calm. And with that machinery in mind, the Pion becomes more than a small particle with an unusual name. It becomes a guide. It leads from the visible world to the nucleus, from the nucleus to the strong force, from the strong force to quarks and gluons, and from quarks and gluons back again to the matter we touch. It is one of those tiny things that makes the universe feel connected across scales. A brief particle that helps explain lasting matter. A messenger made of the same deep force it helps carry. A clue left at the doorway between the atom's centre and the more hidden world underneath. So now we can return to the question we began with, and let it sit quietly for a moment. What is a Pion really? Not just what is it called, not just where does it appear in a particle chart, not just what does it decay into when given the brief chance to exist as a free particle, but what is it in the deeper story of matter? What role does it play in the hidden architecture beneath the familiar world? Why should anyone drifting towards sleep spend an evening thinking about a particle that lives for such a tiny sliver of time that the word moment feels almost comically too large? The answer is that a Pion is one of nature's small connectors. It is not the whole foundation of matter, but it is one of the first particles that helped physicists understand how the foundation works. It is a meson, made from a quark and an antiquark. It is part of the family of particles shaped by the strong interaction. It appears in charged and neutral forms. It is short-lived when produced freely, often vanishing into other particles almost as soon as it appears. But in the effective description of the nuclear force, it also acts as a messenger between protons and neutrons, helping explain how the particles in the nucleus remain bound despite the electric repulsion that would otherwise push protons apart. That is already a lot for such a small particle to carry. If particles had job descriptions, the Pions would require several pages and perhaps a very patient manager. It is not simply a piece of matter, it is a clue. It is not simply a force carrier in the basic textbook sense. It is a bridge between levels of explanation. It belongs to nuclear physics, where protons and neutrons bind into atomic nuclei. It belongs to particle physics, where quarks and antiquarks form mesons. It belongs to the history of science, where Yukawa predicted that a particle like it had to exist. And it belongs to the deeper question of why anything around us has enough stability to be called a thing at all. The world feels solid because many different kinds of binding are happening at once. Atoms are held together by the attraction between negatively charged electrons and positively charged nuclei, shaped by the rules of quantum mechanics. Molecules are held together by electromagnetic interactions between atoms. Crystals, liquids, cells, rocks, and living bodies all depend on those atomic and molecular bonds. But beneath all of that, before chemistry can begin, the nucleus has to exist. Protons and neutrons must stay together. The atomic center must be stable enough to give each element its identity. Without stable nuclei, there would be no periodic table in any meaningful sense. No carbon, no oxygen, no iron, no calcium, no gold, no long chemistry of life. There would be almost nothing for ordinary matter to build with, and the Pion helped reveal why the nucleus can hold. It showed that the strong nuclear attraction could be understood through exchange. A proton and neutron are not simply stuck together by a mysterious substance. They interact through quantum fields. In the older and still useful nuclear picture, pions pass between nucleons as messengers of the residual strong force. That exchange produces attraction at tiny distances. It is short-ranged because the pion has mass. It is powerful because it comes from the strong interaction. It is subtle because it is not the deepest layer, but it remains essential because it describes the force at the scale where nuclei live. The phrase residual strong force may sound like something left behind after the important part has gone home, but that would be misleading. Residual does not mean minor. It means that the force between protons and neutrons is a leftover expression of the deeper strong interaction that binds quarks inside them. The deeper force, carried by gluons, keeps quarks confined inside protons, neutrons, and pions. Then, because protons and neutrons are not perfectly isolated little worlds, the effects of that deeper force extend outward in a limited way. Pions are part of how that extension appears. They are like ripples of the quark and gluon world reaching across the tiny space between nucleons. That is why the pion is such a useful link. It connects the quark level to the nuclear level. A pion is made of quarks, yet it helps explain the attraction between particles that are also made of quarks. It is born from the strong force, and it helps carry the echo of that force between larger composite particles. This is not circular so much as layered. The strong interaction creates hadrons, and some hadrons help mediate interactions between other hadrons. The sea creates waves, and waves carry motion across the sea. The underlying field gives rise to particles, and those particles reveal how the field behaves. This layered view is one of the most important lessons the Pion can teach. Matter is not built like a stack of wooden blocks, with each smaller block simply sitting inside a larger one. It is built more like a set of patterns inside patterns. At one scale, the atom is the useful unit. At a smaller scale, the nucleus and electrons matter. At a smaller scale still, protons and neutrons become the key players. Look deeper, and quarks and gluons take over. But the layers do not erase one another. They talk to one another. The pion is one of the words in that conversation. It is tempting to ask which layer is the real one. Are atoms real, or only quarks and electrons? Are protons real, or only the quarks and gluons inside them? Is the pion real if it lasts so briefly and can appear as a virtual exchange inside nuclear forces? Physics answers in a way that is both practical and profound. They're all real within the context where they make reliable predictions and leave measurable effects. A proton is real because it has properties, interactions, and stability. A pion is real because it can be produced, detected through its decay products, measured and used to explain nuclear forces. A molecule is real because it behaves in consistent ways. Reality is not always reserved for the deepest layer. Sometimes it belongs to the pattern that does the work. The Pion does work. It helps us describe the longest range part of the nuclear force. Long range only by nuclear standards, of course. To us the distance is almost nothing, but inside the nucleus it matters. The Pion is light compared with many other mesons, so its exchange can reach farther within the nuclear scale than heavier meson exchanges. That makes it especially important in binding nucleons. It is not the only part of the nuclear force, and real nuclei are complicated systems with many interactions. But the Pion is central to the story. It is the messenger that lets the strong force reach just far enough to hold protons and neutrons close. And that holding is not gentle in the ordinary sense. The nucleus is not a quiet bundle tied with soft string. It is a dense quantum system, balanced by powerful attractions and repulsions. Protons repel one another through electromagnetism. The strong force pulls nucleons together. At very short distances, other effects prevent them from simply collapsing into one another. Neutrons add binding without adding electric charge. The whole nucleus is a balance, and not a simple one. The fact that it can be stable at all is remarkable. The fact that the universe contains so many stable nuclei, enough to make planets and oceans and living things, is one of the quiet miracles hidden inside everyday matter. The Pion sits inside that miracle as an explanation, not a decoration. Yukawa predicted it because the nuclear force needed a messenger with mass. Cosmic ray experiments eventually revealed it through tracks and decay patterns. The quark model later explained it as a meson, a quark and antiquark bound by the strong interaction. Modern nuclear physics still uses pion exchange as a key part of the force between nucleons. Across every stage, the pion remains a small answer to a large question. It is also a reminder that scientific truth often arrives in pieces. Yukawa did not know the quark structure of the pion when he proposed a meson to carry the nuclear force. The early experimenters who found pion tracks did not yet have the full modern standard model. The quark model itself came later to organize the particle zoo. Quantum chromodynamics then gave a deeper theory of the strong force. Each step improved the picture. Each step corrected, refined, and deepened the earlier one. But the older insight did not simply disappear. It was folded into the larger view. The Pion remained, now understood more richly. That is worth remembering because science is sometimes described as if every new theory destroys the old one. But often, a new theory gives the old one a proper home. Newton's physics still works beautifully for many everyday motions, even though Einstein gave us a deeper view of space and time. The Pion exchange picture still works as a powerful nuclear tool, even though quarks and gluons give the deeper strong interaction. Knowledge does not always move by demolition. Sometimes it moves by nesting, one understanding placed carefully inside another, like boxes inside boxes, each one useful at the scale where it belongs. The Pion's short life also teaches something about the difference between duration and importance. We tend to think that lasting things matter more than fleeting things. A mountain seems more important than a spark. A star seems more important than a flash. But physics does not always agree. A particle can exist briefly and still reveal a law. A collision can last almost no time and still produce data that changes our understanding of matter. A virtual exchange can never appear as a free particle in a detector and yet shape the force between nucleons. The Pion is fleeting, but its role is durable. It vanishes quickly, but the insight it gives remains. The same idea appears everywhere if we look softly enough. A heartbeat is brief, but life depends on many of them. A spoken word disappears into air, but it can change what happens next. A photon from a distant star may be absorbed in an instant, but it carries information across space. Brief things can be essential. The Pion belongs to that family of small passing events that help make larger stability possible. When physicists detect pions, they do not see them directly in the way we see a candle or a cup. They see tracks, decays, energy deposits, patterns. A charged pion may leave a path before decaying into a muon and a neutrino. A neutral pion may decay into photons almost immediately. The particle is known by the evidence it leaves. This is not a weakness. It is how much of deep physics works. The invisible becomes known through its consequences. The hidden becomes real because it changes what can be measured. In that sense, the pion is not only a particle, but also a lesson in how to know what cannot be directly seen. And perhaps that fits the subject perfectly. The pion helps explain forces that are themselves hidden. We do not feel the strong nuclear force tugging on our hands. We do not notice pion exchange as we walk through a room. We do not see quarks or gluons in the objects around us. And yet these hidden things are not remote from us. They are not somewhere else. They are here, inside the atoms of the floor, the air, the body, the blanket, the bones, the page, the tea. The invisible is not distant. It is intimate. It is beneath every ordinary surface. That is one reason particle physics can feel both vast and close. It speaks about energies and scales far outside human experience, but it also describes the matter we're made of. The pion is not part of daily language, but it is part of the story of why daily objects exist. It is involved in the nuclear force that allows atomic centers to remain stable. Stable atomic centers allow elements. Elements allow chemistry. Chemistry allows cells. Cells allow memory, thought, sleep, curiosity, and the quiet question of what a pion really is. The path from pion to person is not direct, but it is connected. So, if we wanted to say it simply, we could say that a pion is a short-lived meson made of a quark and an antiquark, important because it helps mediate the residual strong force between protons and neutrons in atomic nuclei. That would be accurate. It would fit in a science glossary. It would do its job neatly. But the fuller answer is warmer and stranger. A pion is a tiny link between the world of quarks and the world of nuclei. It is a messenger of the force that keeps protons and neutrons bound. It is a clue that matter is held together by exchange, not stillness. It is a particle that appears briefly, but helps explain structures that last for billions of years. It is also one of the reasons the universe is not just hydrogen scattered through space. Hydrogen is beautiful and important, but a universe made only of hydrogen would not have the same richness. The heavier elements require nuclei with multiple protons and neutrons. Those nuclei require binding. Binding requires the strong interaction. And the pion is one of the ways we understand how that interaction works between nucleons. Without the nuclear force, stars would not forge elements as they do. Without those elements, planets would lack their chemistry. Without chemistry, the story of life would never begin. Somewhere behind the complexity of the world is the small, short-ranged work of nuclear binding. Of course, we should not give the pion all the credit. The universe is not held together by one particle alone. Gravity shapes stars and galaxies. Electromagnetism shapes atoms, light, chemistry, and nearly all the forces we feel in daily life. The weak interaction allows certain particles to transform and plays a role in nuclear processes. Gluons hold quarks inside hadrons. The pion is part of this grand team, not a lonely hero. But it is a uniquely important part because it helped reveal how the strong force extends beyond individual protons and neutrons to bind them into nuclei. It is the little messenger that helped explain the crowded center of the atom. There is a kind of humility in that. The pion is not famous in the way the electron is famous. It does not power household metaphors as easily as electricity. It does not glow like the photon, or haunt the imagination like the neutrino, or bend space-time like a black hole. It is brief, technical, and easy to overlook. But the deeper we look, the more often we find that the overlooked things are doing essential work. The hinge is smaller than the door, but the door depends on it. The thread is thinner than the cloth, but the cloth depends on it. The pion is small even among particles, but the story of nuclear binding depends on what it reveals. And now, after wandering through the atom, the nucleus, Yukawa's prediction, cosmic rays, particle tracks, quarks, gluons, and the residual strong force, the Pion looks different from when we first met it. It is no longer just a strange name. It has a place. It belongs to a chain of explanations that leads from the visible world to the invisible machinery beneath it. It helps us understand why the nucleus is not a loose crowd of particles, why protons do not simply repel themselves apart, why neutrons matter so much, why the strong force has such a short reach, and why the deeper quark world still leaves traces at the scale of atomic nuclei. Maybe that is the best way to leave the idea resting in the mind. The Pion is a trace of connection. It is what appears when the strong force reaches from inside one nucleon toward another. It is a particle made from deeper parts, carrying an echo of the force that made it. It is too brief to hold, too small to see, and yet important enough to help explain the matter that holds us. In the quiet of the room, where everything seems still, the nucleus remains bound. The atoms remain themselves. The ordinary world stays ordinary because the extraordinary rules beneath it continue without pause. So when you next see something simple, a stone on a path, a spoon beside a cup, a hand resting under warm light, there is a hidden story there. At the surface, it is matter. Beneath that, atoms. Beneath atoms, nuclei. Beneath nuclei, protons and neutrons. Beneath them, quarks and gluons. And moving between the levels, helping explain how nucleons cling together, is the Pion, small and passing, but deeply meaningful. The tiny link, the brief messenger, the quiet clue that the world is held together not by silence, but by interaction. And so, dear listener, wherever you are, whatever time it is in your corner of the world, let that thought settle gently. The universe is not only vast above us, it is deep within us. Every stable atom is a small act of balance. Every solid thing is a calm surface over hidden motion. Every breath depends on forces far too tiny to feel and far too faithful to forget. The Pion may vanish almost as soon as it appears, but the story it tells remains inside every piece of matter around you. Sleep well, fellow traveller, surrounded by atoms that hold, nuclei that bind, and a quiet universe still exchanging its smallest messages in the dark.